All right, great. So let's begin the class now. Do you have any questions from last week? Any questions from last week?
I'm good.
So far, so good. Any other person who has any questions? Okay. Well, as we go along, if you have questions, you can pause us so that we can answer your questions. Please feel free to stop us. Okay, great. So today we're going to continue with acids and bases. So the first part, as I'll do like last week, I'll do the science and I'll do the math after that. We'll do more math today because we have like our 5 hours today. Okay. And we'll break a little bit in between. Okay. So let's start with acids and bases. Acids and bases. So we want to ask ourselves, what are acids? What are acids? There are several definitions for acids and bases, right? But I'll talk about 3 main ones. And the first one I want to talk about is the definition by somebody called Arrhenius. So we say, call the person Arrhenius. So it's Arrhenius concept of acids and bases. So what does he say about acids? Arrhenius said that acids are substances that produce hydrogen ions or hydronium. So hydrogen ions or hydronium ions in solution, right? So if you see a question that has hydronium, the hydronium is H3O and a plus on it. That's the hydronium, H3O plus. Okay. Any question with that, then you know you're dealing with an acid. Okay. Or if you say hydrogen ions in solution, then there's acid. So this is an example here. If you have HCl, okay, there's an arrow which is missing here, didn't appear. But if you have HCl, it should be like this, HCl plus water, then the arrow, producing the hydronium and then the chlorine. Okay, should arrow in between here. So because this produces hydronium in solution, this is an acid. Okay, put in water, it becomes that. Now the same thing, there's an arrow missing in between this and that. So that should be HCl, it should look like this. And then Cl minus plus H plus. Okay, it should be like this. Okay. So because HCl, when you put it in water, it produces these hydrogen ions in solution that makes it an acid. Okay. So that any of these will make it correct in the definition. Okay. Usually you will put AQ here, AQ. That means aqueous. That means you put it in water, aqua, aqueous, you know, in chemistry. Okay. So that's the first definition for an acid, Arrhenius concept. Arrhenius concept. Then we want to look at Arrhenius definition or concept for a base. For a base. So its definition for a base, Arrhenius concept for base. Okay. He said that a base is any substance that will produce hydroxyl ion in solution. Hydroxyl is OH minus. If you see this in a question, we are talking about a base. A base. Okay. And let's take an example. Example would be sodium hydroxide. Again, there's an arrow missing here, so I'm going to rewrite that. So you have sodium hydroxide. If you put this in water, you have sodium ions plus OH minus hydroxyl. Okay. Then we can put AQ here. That means in solution, AQ, aqua. Okay. Then you are dealing with a base because it produces the OH. This OH in solution. OH in solution. Okay. So dealing with a base. So know the definition for acids and bases. Yeah, we're going to see a lot of questions on that once we finish. Okay. Now, there are other definitions, as I said. We have another one called Bronsted and Lowry. Bronsted and Lowry definition for acids and bases. Okay. And so we'll talk about that. There's another definition by someone called Lewis concept. But we'll not talk about Lewis concept. We'll leave that out. Okay. We'll focus on these two main ones. That's a common one you ask on the test. Okay. So what is Bronsted and Lowry definition for acids and bases? Okay. Now this is the definition. It said acids are proton donors. Acids are proton donors. So proton donors, that means that they produce hydrogen ions in solution. Remember, H plus is a proton, right? Hydrogen is 1, like atomic number has atomic number of 1, a mass of 1. So that means that this has how many protons? It has 1 proton and 1 electron. Remember what we did last week, the number of protons is the same as the number of electrons if there's no charge on the atom. Okay. So if hydrogen loses this electron, if this goes away, then it will just be a proton. It has no electron. So the whole thing is a proton. So that's how it becomes H plus. Okay, it loses the 1 electron. So that's why I call it a proton. Okay. H plus proton. Okay. So that's his definition. Okay. So if you look at this, his definition matches what Arrhenius concept, right? Called hydrogen ions in solution, the same as this proton. So it matches. Okay. Now, not all the compounds will fit under Arrhenius concept. That's why he came up with this definition. And then we see that when we get to the base, that his definition for a base. He said the base is a proton acceptor. Anything that will accept a proton, right? A base, a proton acceptor. Here, acid are proton donors. So they donate hydrogen ions, and then the base accepts the protons. That's the Bronsted and Lowry definition. So what are some examples here? But these are the exceptions to Arrhenius concept. So this one is ammonium, NH4. If you put that in solution plus 4 plus, there's arrow missing here again, it becomes NH3 plus the hydrogen ion. It gives out the proton, gives off proton solution, right? And that's why, so we say this is an acid. Ammonium, this is ammonium ion, okay? Ammonium ion, that's this one. In solution becomes ammonia. NH3 is ammonia. NH3 is ammonia. And NH4 is ammonium. Okay. So anytime you see this ammonium, known as that is an acid. It's an acid. Okay. Then if we turn this backwards, so this here should be NH3. If you take ammonia and then you add hydrogen ion to it, it becomes this here, NH4 plus, becomes like this. Okay, so this ammonia accepts the hydrogen ion, it's added onto it, and then becomes ammonium. Okay, so because this is accepting the hydrogen ion, this is the base. Ammonia is the base. Okay, so that's where the definition comes in. So we don't see OH here, no hydroxyl, So this helps in identifying other acids and bases. Okay, right. So once we know the definition, we can apply it to some other concepts here. So I have here exam tip. You should be able to identify common acids and bases, right? There are some common acid and bases that you should identify. For example, HCl, hydrochloric acid, HNO3, this is nitric acid, and so on, right? H2SO4, sulfuric acid. These are common acids that you should be able to identify. Okay, and if you look here, they are all producing hydrogen ions in solution. When put in solution, what you have here is H2O. The typing didn't come out too clear here, but it's H2O. If put in solution, you put hydrogen ions. I put this in solution, hydrogen ions and NO3 minus. If you put sulfuric acid in solution, you have H3, H plus SO4 2 minus, and so on. Okay, all right. And then when you put these ones are bases, like calcium hydroxide. If you see here, CaOH2, calcium hydroxide, sodium hydroxide, these are all bases, because they can produce OH in solution. They produce OH. Okay. So let me rewrite this here. I think I don't know why it didn't come out too good here. So I have CaOH2. If you put this in solution, it's going to break down into calcium. Usually it's 2 plus. Calcium loses 2 electrons to become stable, or an ion, plus OH. Okay, OH is minus. Okay, so if you balance this, it's like having 2 over here, 2 OH, something like this. Okay, so because it produces OH in solution, this is a base. It's a base. Okay. All right. Okay, so those are some of acids and bases that you should be able to identify. Okay, and then we spoke about Bronsted-Lowry concept already. Lewis concept, I'm not going to dwell too much on that, but just a quick overview of that. Lewis said that acid is an electron donor. Anything that would donate electron is an acid. And then he said base is an electron acceptor. Anything that accepts an electron is a base. That is his definition. So if we take something like Fe, that's ion, the arrows, I don't know why the arrows didn't appear in the notes. They all vanished. So Fe, that's ion, symbol for ion. Remember the symbols for some of the elements too. Fe is for ion. If you put this, this can give off 2 electrons. We write it like this. So ion can donate 2 electrons to become F plus, F2 plus, right? So from here to there, it has lost an electron, lost 2 electrons. If you write 2e minus 2 electrons, that's what that means. So because it has lost electrons, it means it's donating, right? It's donating electrons. Because this can donate electrons to become Fe2 plus, this ion here is an acid. It's an acid. Okay. If I go backwards, so this is an acid here. It's called a Lewis acid. If you go backwards, if I take Fe2 plus and I add 2 electrons to it, now the 2 electrons will neutralize the electron loss here, and then this becomes neutral, becomes ion without a charge on it. All right. So this one, because this can accept this ion can accept 2 electrons to become the ion, neutral ion. This is a Lewis base. Okay, it's a Lewis base. Okay. So those are some of the applications of this. But the first 2 concepts is what you should really focus on for your test. If you go in chemistry proper, then you do more of these. Okay. All right. So enough of the definitions. Okay. I see something here. Okay, this one was used to illustrate the Lewis, another Lewis concept. this should be minus here. Okay, this should look like Cl plus 1 electron to give you Cl minus. This is how it should look, this one here. It should look like this. So chlorine atom accepted 1 electron, right? It received 1 electron, so accepted, and it became chlorine minus, the ion. Okay, because this accepted the electron, this chlorine here is going to be a Lewis base. Lewis base, because it's accepting electron. Okay, so that's how to apply the Lewis concept. Okay, it's a Lewis base. Okay. As I said, focus on more on the first 2 concepts. Okay, right. So let's go to how to test for acids. How do you test for acids? Very important. Again, the test, they like this type of questions. Okay. Now, acids would always turn blue litmus paper red. Acids turn blue litmus paper red. Okay. So take an acid, you have, and you have what you call a blue litmus, a paper which has some chemical in it and it's blue. If you put in acid, anything that's an acid, it should become red. If it turns red, then you know it didn't have acid. Whilst the opposite is for base. When you have a base would turn red litmus paper blue. A base would turn red litmus paper blue. So a base turns red litmus blue. Base will turn red litmus paper blue. Okay, so if you have that, then you know you're dealing with a base. So these are 2 important things to remember. Okay. All right. Now, how do you measure the strength of an acid or a base? Measurement of the strength of an acid or a base. Okay. Now, to measure the strength of an acid or base, we use what we call a pH scale. So pH scale, we use what we call the pH meter. The pH meter gives you the scale. So pH measures the strength of acids and bases. Okay. So that's what a pH scale will do. Okay. And what is the pH? The pH is the negative log. So have that here. pH is a negative log of the hydrogen ion concentration. Okay, that is hidden under this picture. So I'm going to rewrite that out. Okay. Some of the things end up shifting on this notes. Okay. So I'm going to rewrite that out. So pH is equal to the negative log of the hydrogen ion concentration. When you use a bracket like this and you write something in it, an ion in it like this, it means concentration in chemistry, right? Concentration. So it's a negative log of the hydrogen ion concentration. That's pH. Okay. And once you take this negative log, you come up with numbers that range from 0 to 14, right? Which we call the pH scale. pH scale. So the pH scale ranges from 0 to 14. Okay, because pH scale. Okay. So it's going to look like this. 0, 7 in the middle, and 14. Right? If the pH is 7, it's neutral. So that's a neutral position. You know, like water will be here. And then anything below 7, from 7 down, towards the left, you have increasing acidity. It becomes more acidic the smaller the number. So here we have increasing acidity. And anything more than 7 and above, up to 14, this is increasing basicity or alkalinity. Increasing basicity or alkalinity. Alkaline the same as like base. Alkalinity. Alkaline or base. Okay. So that is how the pH scale can be interpreted. Okay. So anything that's pH of around maybe, if you use a cutoff here, let's say around 5, between 5 and 7 will be like a weak acid. Anything like say around 0 to around 4-ish, there will be like a strong acid and so on, right? If you can use 4 as like a cutoff around there. Okay. 4 and above, like a weak, and then strong. The same thing if you come to the base zone, between 7 and 14, anything close to 7 will be weak. So let's say up to around something around the 10 area will be like strong, it will be weak, and 10 and above, you know, like a strong base, and so on. Closer to 14, stronger. Closer to 7, weak, you know, something like that. Close to 0, strong acid, and so on. Close to 7, weak acid, etc. Okay. So sometimes they give you questions where they ask you to identify which of the following is a weak acid and strong acid and so on. You know, and they give the pH to use. As I said, we'll be seeing some questions like that shortly. Okay. So this diagram that I have here shows you some substances and their pH, like, you know, like water around 7, Coke, you know, that very acidic. It's around here, very acidic, you know, and then some other things. You can compare the acidity to give some idea of what the pH values mean. Okay. All right, so I have all that I've said. I have the definitions here. pH is a measure of, to describe the degree of acidity. I have this here. It's measured on the scale of 0 to 14, as I said. Formal definition is negative law of hydrogen concentration, which I have here, you know, and so on. Okay. All right. Okay, good. Another diagram that shows you the acidity of different things, just to give you some perspective on what pH means. Okay. All right. Okay. Stomach acid, very acidic. Look at where it is, around here, around 1. Whereas lemon, around 2, and so on. Grape, around 3, etc. Pure water, around 7. Bleach, around 12. See? Baking soda, around 9, and so on. So it gives an idea, you know, in everyday life. Okay, right. So I have some questions that I want us to practice on the pH. Okay, so let's look at the first question. Say, if hydrogen ion concentration of a solution is 1 × 10⁻⁻⁵, what is the pH of the solution? What's the pH of the solution? Okay. Now on the test, I always say that they'll give you simple problems that you don't need to use the calculator at all. You know, I mean, even though you can use it, but you don't need to in some questions. They don't make it complex. for you to use it like a scientific. No, just a regular calculator will be given to you. So if hydrogen ion concentration of a solution is 1 × 10⁻⁵, what is the pH of the solution? I want to find the pH of the solution. Okay. Now, if I have a problem like this, I'm not going to waste my time working it out at all. So I'm going to do it the long way, and I'll show you the quick way to do this, at least for you to understand what's happening. Okay. So here the pH has been given, right? No, we're given the concentration. You want to find a pH. So I'm going to write it down. pH is equal to the negative log of the hydrogen ion concentration, right? That's the normal way, to long way. So I know the concentration is given. It's negative log of, that is, this is given here, 1 × 10⁻⁵. Anything 1 times something to the power -5 is the same as itself. So it's 1 × 10⁻⁵. This is the same as saying negative log of 10⁻⁵. Any number times 1 is the same number. Okay. If you remember the properties of log from your math class, if you have an exponent, you can always bring the exponent in front of the log. Okay, you can bring it down. It's one of the properties of exponents in log. You can bring it in front here. It becomes a coefficient. Okay, so I can rewrite this as negative of -5 times log 10. Now, what is the log of 10? Log of 10 is always equal to 1. So you have 1, this is negative becomes positive, so I have 5 times 1, which is 5. So the pH here is 5. So the answer is 5. That's the pH for this question. Okay. All right. So far I've done it in the regular way. You know, if you're given a question, regular question in chemistry to do. Okay. Now, but as I said, the test will always be something that you can do easily. Okay. So if I see this question, right, any question that has 1 × 10⁻⁵, 1 times something times 10 to something, I'm not going to waste my time doing what I did. You know, all that you have to do, if you look at what's happening here, all that you have to do is just to go to the exponent. Think about the exponent here. And then take the opposite of the exponent. Take the opposite of the exponent. So if you take the opposite of the exponent, take opposite of the exponent. Okay, and then that will give you the pH. So the exponent here is -5. Because I want a pH, I take the opposite of that and I get 5 as the answer. It's going to work out for you when it is 1 times something. If it's not 1 here, then it will not work out. Then you need a calculator to really do the log, you know. So always look out for 1 times something to the power times 10 to the power, something. Then you can do that. Okay. So for example, number 2, say if the hydrogen concentration of the solution is 1 × 10⁻⁵, what can you say about the solution? Would somebody want to try that one?
It's a strong acid.
It's a strong acid. Perfect. It's a strong acid, right? So because I see 1 × 10⁻⁵, I can quickly go to the exponent and look at it. -3. So -3, if I take the opposite of that, is 3. So the pH is 3.
3.
Yeah. Now think about the scale, the pH scale. We said that this is closer to 0 because close to 0. It's a strong acid. So she's correct. Strong acid, B. So that's how you can use this idea quickly. So you don't have to go do the long thing that I did here, You only do that if there's no one. Let's say if it's two, then it's not going to work out the way I'm talking about. You have to do the full calculation like I did. Okay. And you need a calculator to really do that part. Okay. Now they always give you one time something, you know, just to test you. All right. So far we are dealing with hydrogen ion concentration, right? That's what we're doing here. Okay. Now for number three, it's similar, but we have to be careful here with the information given. Now, if you look here, this time I'm doing what we call hydroxyl concentration. Hydroxyl concentration. Okay. Now, when you're getting the hydroxyl concentration, we can find what we call the POH, right? POH is like a pH type of thing, but now POH. Now, POH is also similar. So POH is the negative log of the concentration of the OH ions. Okay. So they give you hydroxyl, you can find the POH, right? Once you know the POH, then you can find the pH. The relationship between pH and POH is this. If you have the pH plus POH, it's always equal to the number 14, right? So you have to keep that in mind. So if I know the POH, if I subtract from 14, then I get a pH. The same thing, if I know the pH, if I subtract from 14, I get a POH, right? They go hand in hand like that. They complement each other to get a 14. Okay. So for a question like this is the hydroxy ion. So it means that I can use this information like we did against 1 times 10 to the power negative 5. So quickly, I can look at the exponents and take the opposite exponent. So my POH in this question will be equal to positive 5. You know. Then I want a pH. You want a pH. So what will be the pH? Now the pH will be equal to 14 minus the 5. And then that will give us 9. So what I'm dealing with has a pH of 9. A pH of 9. Yeah, like that. If I know the POH, if I subtract from 14, it gives me the pH. Okay. So take like a minute to tell me what number 4 will be. Everybody should try that and let's see. Number 4.
Would it be a weak
Strong
base?
base. Strong base.
It says strong base.
Strong base, yeah.
Okay, somebody said a strong base. Did you all get that or somebody had something different?
Wouldn't it be a weak base because it's closer to 7?
Okay, some also said a weak base close to 7. All right, so let's all see. Let's try and see. So here we'll be given the hydroxyl ion, all right, it's concentration. Okay, and it's 1 times 10 to the power negative 3. So I can apply a quick plan. Okay, so it means the POH, since we're doing hydroxyl, over here is positive 3, negative of that. So it's positive 3. Okay, so what will be the pH? The pH here will be 14 minus 3. That is 11. Okay, so it's 11 a strong acid or base or weak base or strong or weak acid.
Be strong.
Strong base.
A
Yeah,
strong base.
it's close to 14, right? So it's a
Yeah, so it's a
strong
strong
base.
base.
So this is a strong, it should be D, strong base, strong base. Okay. So that's how you apply all that I've said so far. A strong base. Okay. Great. So does anybody have a question on what you've done so far? So the key thing is you look at what are they asking? Did they give you hydroxyl concentration, or did they give you the hydrogen ion concentration? Right. Those are things you have to look out for. Right? If hydroxyl, then you can find the POH. If you know the POH, subtract from 14 and get a pH. Then you can compare to the table, the scale. You know. All right. Anybody has any question on so far? All right, so that's another type of question that could be asked, on acids and bases.
Professor, how would you
Yes,
know? How would you know if it's a what is the range of a weak base again?
remember the pH scale
Yeah,
from
it's
0 to 14, right? If you go back to the scale that I drew,
yeah for the weak base. I mean, like
yeah, right,
the
right here.
range of 7 to
Yeah, so 0 to anything greater than 7 is a base.
yeah. If it's
Anything less than 7 is an acid,
okay.
right? And then if it's closer to 14, let's say 10, 11, 12,
Oh, 10, 11, 12 is a strong base.
yeah, you can use like a cutoff in between the middle as your, to distinguish strong and, in those range. So between 0 and 7, around 4, right? Around 4 would be the cutoff. Anything less than 4, like a strong, above 4 to 7 area, like a weak acid and so on.
Okay, thank you.
Okay, good. All right, great. So that's, okay, there's one more type of example that I want to give. There's something missing on this slide. I don't know why when you save it and something's missing for some reason. I have to check that again. But there's one important thing which is missing on this paper. I think it should have been here. So it didn't appear here. Okay, and that is neutralization. So let's go over that. Neutralization reactions. They also like those type of questions. Neutralization reaction. Okay, so when you say neutralization in chemistry, we're talking about the reaction between an acid and a base to produce what we call a salt and water, salt plus water. That's what we call neutralization, salt plus water. Okay, so if you don't see an acid, you don't see a base, you don't see a salt, you don't see water, it cannot be neutralization. Okay, there are some questions in the book that we'll see later. Okay. For example, if I have HCl plus sodium hydroxide, so this is an acid and that's the base, right? You form the salt that will be formed will be Na. So this sodium goes to chlorine, so it becomes sodium chloride, and then plus the water. Water comes from H and OH, H2O. Okay, so this is neutralization: acid, base, salt, and water. Okay. I'm going to make up another one. H2SO4 plus, let's say, potassium hydroxide. So that's the base and that's the acid, sulfuric acid. Okay, the salt that will be formed will be between potassium and then the sulfate. So we're going to have K. Usually potassium needs 2, you need 2 of that, and then 1 sulfate. So that's potassium sulfate plus water we form from this and that, H2O. Okay. If we balance this, we should be able to balance reactions too. You have 2 potassiums here, so it means I need to have 2 here to balance that. So I have 2 potassium, that's correct. Sulfate 1, and then the H2O, let's see how many. 2 hydrogens here, 2 there, and that makes it 4. But I have 2 here, so I have to multiply this by 2. And then O2, 2 of that, and 2 of the oxidants. So this is balanced. Okay, so these are all examples of neutralization reactions. Okay, acid, base, giving you a salt and water. If you don't see that in any reaction given to you, it cannot be neutralization. Okay, all right, great. Any question on neutralizations? Okay, so this should complete the topic on acids and bases for now. Okay. You should be able to answer any question given to you. on this. Okay. All right, so far so good, I believe. Okay. All right. We'll see questions later, more questions. Okay, so let's move on to the next topic then. All right, so I'm going to go to the second handout that we have for today. And today I'm going to talk about blood. After that, we'll talk a lot about physics. I want to introduce you to physics. So let's finish up with the blood here and then get rid of the biology and anatomy physiology here. Okay. We all know a lot about the blood already, so that'll be quick. Blood composition and functions. We know that the blood is composed of plasma. The plasma is the liquid part of the blood and what we call the formed cells, right? Plasma, liquid parts, and they had a formed cells. So let's say blood, if you had the blood, you have plasma and the formed cells. Formed cells, right? So the formed cells are like the blood cells that we're going to talk about. The plasma makes about 90 to 92%. It's made up of 90 to 92% of water, and you have a lot of things dissolved in it, right? Gases and nutrients like oxygen, carbon dioxide, you have nutrients, glucose, fat, amino acids, you have salt in it, you have proteins like fibrinogen, albumin, immunoglobulins, hormones, they're all proteins in the blood. And then you have other waste, nitrogenous waste like uric acid and urea. So these are waste substances in the blood. They all dissolve in the plasma. Okay, all right. Now the plasma has two components. We have what they call, it is serum, and then the other part is fibrinogen. Okay, the fibrinogen. Okay, now this serum is the part of the blood that does not clot, right? Fibrinogen makes the blood clot, so it's involved in clotting of blood. Fibrinogen. Okay, it's an inactive form, very inactive protein. It has to be activated to what we call fibrin before the blood can clot. So fibrin is what clots the blood. So active, it's the active form, and that's what causes the blood to clot. Okay, this is inactive. Anything with O gene attached to this is inactive protein. Okay, it has to be activated by a series of processes, very complex process, which you do in physiology. Okay, so if you take out the fibrinogen from plasma, they have serum. Okay, so if somebody's having like clotting problems, you don't want to give the person serum, because the serum will not make the blood clot. Either you give the person plasma or something like whole blood. If you give whole blood, that's fine, or the plasma, because the plasma contains the fibrinogen. Okay, you don't give the person just serum in the hospital. Okay, if the person's clot, like it has the blood does not, if the blood doesn't clot, you give a person plasma or something that has fibrinogen in it. Okay, right. So let's talk about the blood cells. The blood cells. Okay, so we're under the formed cells. So under the formed cells, you have the red blood cells. Another name for red blood cells is the erythrocytes. Remember, erythro means red. Erythro is red. Okay. Then you have the white blood cells. Known as a leuco. Leuco means white, leukocytes. And then we also have the platelets. Known as a thrombosis, clotting, thrombocytes. So these are the form cells that we have in the blood. When you're studying, you have to know the functions of these cells because they ask those questions. Functions of the cells. Okay. So the main function of the red blood cell is to transport oxygen. Oxygen transport. So function, oxygen transport. In the blood. So it carries oxygen in the blood. Okay. Now the oxygen is carried by the hemoglobin. We have hemoglobin in the red blood cell. So hemoglobin carries the oxygen. Okay. It carries the oxygen. Okay. And then remember that if somebody has reduced amount of oxygen, hemoglobin, then the person is said to be anemic, right? So anemia is reduced amount of hemoglobin in the blood, anemia. So at least know what that is. Okay. And a mature red blood cell have no nucleus. They have no nucleus, matured one. When the young ones have nucleus, but nucleus is pushed out as it matures. Okay, and it's the place is place taken by the hemoglobin. So it's good to know that matured red RBCs, red blood cells, have no nucleus. Good to know that. Okay. Okay. Now, the red blood cells also carry some carbon dioxide, but it's tiny, just a small amount. Most carbon dioxides are carried, transported in the, like they're dissolved in the plasma. Okay. Then when it comes to white blood cells, the general function of white blood cells is to fight infection, right? The general function, they fight infection, right? But there are different types. So I'll break it down to the types. You can classify the white blood cells based on how they staining technique. So based on the staining, you have what we call the neutrophils. You have the eosinophils. You have what we call the basophils. Okay, so eosinophils pick up the acid stain. Basophils pick up what we call the basic stain, basophils. So they appear like bluish or purplish, basophils. Neutrophils are neutral. They don't pick up any stain. And then you have the lymphocytes. And the last one is the monocytes. So these are different types of white blood cells that you come across, different types. Okay. Now, what are the specific functions? We can break them down. Now, there's neutrophils. They mainly fight off bacteria. They fight bacteria, so bacterial infections. Fight bacterial infections. Okay, bacterial infections. Eosinophils, they tend to play a role in fighting parasitic infections. Fight parasites. So that's one of the functions. And then they also play a role in allergies. So allergic reactions. They play a role in allergies. Okay. Now, basophils, they are also involved in allergic reactions, allergies. Okay. So some of allergies, you see the levels go high. Eosinophils, for example, go high. Somebody has asthmatic attack and so on. It goes high up. Then lymphocytes, they play a role in fighting of viral infections. So fight of viruses. Okay. Yeah. So if somebody has, let's say, an HIV infection, usually the level of their there are different types of lymphocytes, right? There are different types, but one of the type goes down, it's suppressed. You know, you have what we call it T helper cells, and you have suppressor cells, cytotoxic T cells, and so on. You know, you have T lymphocytes and have B lymphocytes, two types, B and T, and under each one there are different types as well. T has different types, you know, so on. Okay. But in general, they fight off viruses. And then the monocytes are like scavengers. They come to clear the site of infection. So once all these other ones have finished their job, then they come to the site and then they finish up the work that is left, you know, in fighting off all the infections. So they clear the site of infections. Clear the site of infection. Okay. So they're like scavengers. Okay. And then they also help to fight off like cancer and so on, cancer cells. So clear the sites of infection / cancer. Okay, something like. Okay, so those are the specific roles that these cells play. So, but in general, when they ask you what's the function of the white blood cells, they fight off infection, right? That's the main role, fighting infection. And then when it comes to platelets, the function of the platelet is for clotting of blood clotting of blood. Okay. So they form like plugs that block in its ruptured vessel. Now remember that the platelets are not cells. Platelets are not cells. They are fragments of cells or fragmented cells. But they are not actual cells. Okay. So these are some key points which, if you know, I believe should to answer questions on the blood that they ask you on the tests. Okay. Any questions on the blood? Quick overview.
Professor, please, I have a question.
Yes, please go ahead.
Yeah, what's the difference between the platelets and the thyroglobulin, the other one? Because they all have clotting. Yes.
Perfect. Good question. Right. So the platelets, think of them like plug, right? So if your blood vessel, there's a cut somewhere and you're bleeding, the fibrinogen comes in there to form a network, like a mesh, like think of like a net. So the fibrinogen is changed to the fibrin, and then that comes to form the net at the site of the cut. Now the platelets are like plugs, so they will be trapped in the fibrinogen, the network or the fibrin that is formed, right? They're trapped in there. So those are the distinction. You know, the fibrinogen is a protein.
So they initiate the clotting, the floating to, they initiate the platelet to clot, right?
I'll say, yeah, partly. It's a very complex mechanism that occurs there. A lot of what you call the clotting factors. I don't know if you've heard of the clotting factors. There's so many clotting factors that come into play. But the clotting factors are all inactive, but they're activated once you have a cut, and then your epithelium in the blood vessel is like once it's exposed, right? The cut off is gone, and it activates quickly. It activates what we call the clotting factors, and the clotting factors will activate other clotting factors. It's a very complex mechanism. And then at the end, it will there's something called thromboplastin. Thromboplastin that is going to activate the fibrinogen and then change it to fibrin. And then the fibrin will form the network at the site of the cut. You know, and then the platelets will now be trapped in there like a net trapping fish type of thing. You know, once they trap, they block all the spaces that you see in the net, and then that stops the. So it forms like, let's put it there, the fibrinogen forms like a scaffold, you know, like a scaffold for the platelets to hang on, something like that, to form the block, you know. And as time goes on, the fibrin hardens, and then it shrinks. As it shrinks, the block becomes harder and harder. You know, that's why you cut yourself. Initially, it's a little bit soft. As time goes on, it becomes harder and harder and harder. But the fibrin shrinks, you know, and so on. Yeah. If you get a chance, you know, you're welcome. Yeah. If you're interested in reading more, if you Google like clotting mechanism in the body, it's very interesting thing. I encourage all of you to, if you get a chance, to read about it. And you're going to need that in your nursing class, pathophysiology and physiology. You know, very important to know that. So good question. Okay. Right. Any other questions on this? Okay, great. So I believe we have enough information to be able to practice some questions later. Okay. Right. Now I want our mind to switch to physics today, a little bit of physics. We'll not do all the physics, but most. And I always tell people when I take the polls, I know a lot of people, you know, physics, they've not done physics. Usually I don't get any, if out of maybe 12 or 15 people, I don't get anybody who has done physics before taking this test, you know. But chemistry, biology, yes, a lot will do that. For some reason, people don't take physics these days. Probably, I don't know, maybe in high school they do, but after that, they throw it somewhere. But the test has a lot of physics in it as well. You know, I've forgotten the percentage that they have, but it's on, I think it's on their website. You know, maybe about 15% or something, or 20%, somewhere around there. So you have to know physics. So we'll begin with the introduction to mechanics, motion, and forces. The questions that they ask you are very simple, straightforward, if you know exactly what they're asking about. So our attempt to make it simple for you to understand, and even though you may not have covered any physics in many, many years. All right, so rest assured, you will understand a lot of things today before you leave. So let's begin with mechanics. Now, the first thing I want us to talk about is the laws of motion, Newton's laws of motion, which I believe you've all heard before. So we'll talk about that, and we'll talk about some applications that they ask you on the test. Now, the first law of Newton's first law, okay, it says that an object at rest will remain at rest, and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. Okay, or some people put it, unless acted upon by an opposing force. Okay, force acting in opposite direction. Okay, what does this mean? It means that if I leave a book on the table and I come back a million years later, that book will still be on the table unless there's an external force that acts on it to move it. Otherwise, it will be there forever. Likewise, if passengers are in a bus move at the speed of the bus, they move at the same speed as the bus, right? Once you're in a bus as a passenger, you move the same speed as the bus is moving. Now, when a bus comes to a sudden stop, passengers will keep moving or thrown out in a straight path at the same speed, and they will only be stopped by the windshield, which will be the opposing force. Okay, so what we are saying is that you move the same speed as the vehicle. So if the vehicle stops suddenly, you still keep moving at the same speed. You keep moving forever. The only thing that stops or will stop the person is the windshield. If there's no windshield there, then he's saying that you keep moving forever, nothing will stop you. Okay, so the opposing force is the windshield which stops the person. Okay, that's its law. So they give a scenario like this, then you know they with the first law of motion, Newton's first law. Okay. Then the second law. The second law is a mathematical formula that you have to know. It says force equals mass times acceleration. Force is the mass times acceleration. Putting this in words, what he said was that the force on an object is directly proportional to its mass and also directly proportional to its acceleration. In other words, if you take a particular force acting on an object, if the mass is high, then you expect the force to be, what should I say, high force, right? And then the acceleration, if the acceleration is high, you expect the force to be high as well, because they are proportional. If you increase acceleration, you increase the force. If you increase the mass, you increase the force, and so on. That's what he's saying, right? But between the mass and acceleration is an inverse relationship. In other words, if I take a particular force, if I increase the mass, then the acceleration will go down, all right? And then for the same force, if I increase the acceleration, the mass has to go down if I have to maintain a particular force, right? That's what it's saying, you know. So mass and acceleration is an inverse relationship. But when you take force and acceleration or force and mass, it's a direct proportionality. So know this formula. Force is equal to mass times acceleration, right? And then we'll put the short form F is equal to MA. You're going to use that to answer questions along the line, okay? So they give you the mass and they give you the acceleration, it's your way to find the force. Or they give you the force and then you know the mass, it's your way to find acceleration and so on. Two knowns, you can find a third unknown, you know. So keep this formula somewhere handy. And then I explained the second law here for you to understand. Okay. But we'll come to this again. Now remember that force is like weight, right? Weight. Weight is a force. Weight is a type of force. So you have to know the difference between mass and weight. Mass and weight. Does anybody remember the difference between mass and weight?
Mass is how much space an object is taking, and weight is how hard gravity is like pulling down on you.
Yeah, yeah, correct, correct. Right. So what she said is correct, right? But I want to add the fact that mass is constant, right? Mass doesn't change, and but weight varies based on the gravity because it's the effect of gravity on the person. So weight varies due to the gravity. In addition to what she said. Okay. So when you go to the moon, the content in you doesn't change. So you have the same mass on the moon, because the mass your content in you, the content in you. Whilst the weight is a type of force that depends on the gravity. So if you go on the moon, the gravity is zero gravity. So the person feels weightless, even though you have your mass, you feel weightless because the force on you is zero. Okay. So again, it comes from a formula. So F is equal to, so ma. This time the A will be G. G is acceleration due to gravity. You replace A with a G. So when you use G, acceleration due to gravity. Okay. So weight is a type of force. If you like, instead of using this, we can say W, the weight is mg. We're dealing with weight. The weight is the mass times the gravity. Okay. So since gravity is zero on the moon, if I replace it with zero, then it means that no matter the mass, the force on you will always be zero. Okay, you feel weightless. That's why the astronauts float. You feel weightless, zero gravity. Okay. All right. So keep this formula handy. But there's a question, I don't know where I saw it some time ago. I've not seen it in a while somewhere, but they give you the weight of the person. Let's say somebody weighs 70 kilograms on the earth. And then they said the person went somewhere, like somewhere where the gravity is 1/7 of that of the earth. What is the weight of the person? So if you know the weight, you multiply by 1/7 of, then that would be how much the person is going to weigh. It's 1/7 of that. Now the figure for acceleration to gravity, the actual figure, it's a long number, but usually we use the G is 9.8 meters per second squared. That's the acceleration due to gravity, right? But in problems, because they always want to make your life easy, they'll more like approximation. So it's approximately 10 meters per second. We can use this for calculations, approximation. If you have to work out problems, most of the time they said approximately what's the weight of the person, Since most of the time the things they use, they expect you not to use a calculator too much, So they like you to round things. So if you use 10, it will give you the answer that you want. Okay. Unless you want the actual number, there's 9.8 something. Okay, right, good. And then the third law of Newton, it says action and reaction forces are equal but opposites of each other. In other words, say for every action, there is an equal and opposite reaction. Equal and opposite reaction. The action force is the applied force, and the opposing force is called the reaction force. Right? So what, as the explanations here, say if I push on the wall pushes me back with the same force acting in the opposite direction. So if I push the wall is just pushing me back with the same force. If the wall doesn't push me the same force, that means that I'm going to break the wall. And the wall pushes me back with a force greater than the force I'm using, then the wall is going to push me. right? Since the wall is not moving, it means that it's applying, the wall is also applying the same force on me. That's why I can break the wall. Likewise, as I stand on the floor or the ground, I'm not sinking. Why? Because my weight, which is the force, is balanced by an opposite force, which is the reaction force from the floor. The floor is also pushing me up with the same force. That's why I'm standing. Otherwise, I have to sink if my weight is greater than the force of the floor pushing me back. And if the floor is pushing me with a greater force than my force, then it should throw me up. Okay. But I'm standing. That means that the forces are opposite, equal but opposite, balance each other. That's the idea he came up with here. Action and reaction forces are equal but opposites. Okay, all right. So those are the type of, the laws that you should be thinking about. And they give scenarios, you should be able to tell which law that is being applied. Okay, so that's the first aspect of the motion. Okay, so some calculations, I've put down some calculations here to see how we can apply it. So the first one here, let's look at that. It says the engine of a train of mass 800 kilograms, which is traveling along a straight horizontal line, is producing a force of 1200 newtons. Okay, I'll talk about the units very soon, the unit of some of these things. Assuming that there are no forces resisting the motion, calculate the acceleration of the train. So here you've been given the mass, all right? You need the mass. You've been given the force. Now they say find the acceleration. Okay. So quickly we have to think of a relationship. Force is equal to mass times acceleration. So I write this down like that. Now, since I want acceleration, it means that I have to divide the force by the mass, right? And so if I do that, I get 0.5 meters per second here, okay? The unit for acceleration is meters per second, right? Remember, something per second, that's acceleration. Okay. So that's how you can use a formula to work this out, okay? Oh, I think I put in the wrong numbers here, sorry. Yeah, I put 1500, this should be 1200 here. So let's do that again. So A should be equal to it's not 750, 800. I copied the wrong things I put down here. Okay, so this is not the correct numbers to use here. So it should be, force is 1200, so this is 1200 divided by 800, yes.
1.5.
It's 1.5, right?
Yes, 1.5.
Okay, thank you very much. 1.5 meters per second. I always said I have to change this thing. I always end up forgetting to change it. Okay, thank you very much on that. Okay, so 1.5, great. All right, so the idea is to know how to use the formula. Okay, when you come here, do I have the correct one? Okay, so here I think I have the correct one here. So the tension is just like force. When there's tension is like the force on the object. So it's the same process, You find it, so divide the force by the mass, and you get acceleration here. Okay.
0.5.
0.5, good. So that one is correct. Great. Right. So that's how you can apply this particular formula and the concept. Okay. Right. Does somebody have any question on Newton's law and application?
Please, I have a question.
Yes, please go ahead.
Will you always be giving the formulas, or you should know it at your fingertips? Like you should know the formulas before.
Oh yeah, I mean, you should know the formulas. They will not give you.
Oh.
Yeah, you should know the formulas. And I mean, basically, they are straightforward. The way they made a test, they don't expect too much of you to formulas, like basic formulas like this, force, distance formula, velocity, basic formula, like the electricity. We'll do electricity. No, we didn't do electricity. We'll do that today. We'll talk about that, and you see some formulas, general formulas that you need to know.
Okay.
Yeah. Okay. All right. So let's talk about some quantities that are used in science. You should also be able to identify some of them in questions. There are two main quantities that we use in science. One of them is called a scalar, and the other one is known as a vector quantity. So a scalar and vector quantities. When you say a scalar quantity, that quantity has only magnitude. So magnitude, another word I'm going to write down here. So let's say size. You're only interested in the size. Okay, that's a magnitude. Now, when you say a vector quantity, you're interested in the magnitude and direction. Magnitude and direction are important. Let me give you some examples. Okay. Now, an example of scalar quantities is length, area, volume, speed, mass, density, temperature, pressure, energy, entropy, work, power. Those are all examples of scalar quantities. So when they ask you a question, you should identify them. These are scalar quantities, right? Why? Let's take something like, let me add distance here. The length is distance, right? So, but let me put distance here. Because it's the same, if you talk about length, we're talking about distance for a reason. So let's talk distance. If I tell you that I traveled 2 miles, that is a scalar quantity, 2 miles. Or I traveled 10 meters, scalar. I did not tell you my direction. I just told you the size or the quantity, the magnitude. So that's a scalar quantity. Okay. Now the same thing, I can come, let me write that here. So let's say I say 20, let's say 20 miles. Okay, here. Now when I come here, vector, example of vector quantity, displacement, direction that you move in is very important. Velocity, acceleration, momentum, force, electric field, magnetic field, they are all examples of vector quantities. So let's talk about displacement, right? Now displacement is like distance, but then I have to specify the direction. So here I have to say something like I'm traveling, so I traveled maybe 20 miles, maybe west. Then that becomes my displacement. So that is a displacement here. 20 miles west, displacement. Direction has to be specified. The same with speed and velocity. Speed is a scalar quantity. So for speed, I can say something like I'm traveling, let's say 10 miles per hour for the speed, right? Speed here. 10 miles per hour. Now, when I come to velocity, velocity is like speed, but then I have to state my direction. So in terms of velocity here, I have to say I'm traveling at the speed of 10 miles per hour, maybe west or north or something. I have to specify the direction. Very important. And that becomes a vector quantity. Okay. Let me give you one example here about distance and velocity. Okay, let's say that this is my starting point. You see, this is where the negative and positive sign comes in the number line. So a starting point. So let's say 0.0. And then I move to a town here, and that town maybe is 10 miles away. I move to 10 miles away, so 10. Towards the west, right? No, this is east and west, so that's east here. East, okay. And then from here, I move back to where I started from. What will be my distance, my total distance? Total distance. Now the total distance here will be 10, and then back, another 10 back. So in all, I traveled a total distance of 20 miles. Total distance 20 miles, okay. Now, what about my displacement for the same thing? Total displacement. Total displacement. Direction is important. So the direction will be indicated by negative or positive sign, right? So if I go towards the right, toward the east, I'm moving in a positive direction. So 10. I went 10 towards the east, plus. Now I'm coming backwards. I'm going towards the west if I'm returning. So it will be negative going towards the left side. So it's negative 10. That means opposite direction. What would this give me? I'll get 0 miles. So my displacement here is 0. Okay, 0. Two different things. So displacement is different from distance. Okay, even though people interchange the two in life, but they are two different things to the scientist. Direction is important. Okay, so this means that in reference to the starting point, as if I've not moved. If somebody saw me here, and then in the absence of the person maybe went somewhere and I've traveled and came back. If the person comes back later, you're still going to see me standing at the same place as if I didn't move. Okay, so displacement is in reference to a starting point. 0 from a starting point appears as I didn't move, but I cover a total distance of 20 miles. Okay. I hope that explains the difference to you well. Okay. All right, so know some of the examples, as I said. So when they ask you which of the following quantities is vector, scalar, you should be able to answer them. Okay. All right. All right, so some important formulas to know. Some important formulas. For distance, remember distance is speed times time. Speed times time. Some people say rate times time from math classes, rate times time, or the speed, because speed is the rate. Rate times time. Work is defined as force times distance. I'll ask you some interesting question under work soon. Work done is force times distance, the amount of work done by anybody. If they give the force, you multiply by distance, you should get a work done. Okay, so keep this also in mind. Then acceleration. Acceleration is a change in velocity over change in time, right? So we have final velocity minus initial velocity over final time minus initial time. That is how you calculate acceleration. Acceleration. So it's like, you think of slope when it comes to acceleration. So it's like your y2, so we can say v2 minus v1 over t2 minus t1, something like that. The slope, y2 minus y1 over x2 minus x1. Okay. Because one of the questions that they ask you is they give you a graph. So I drew this graph here. They give you a graph where you have the velocity on the y-axis and then time on the x-axis. Now here, positive slope. Remember positive slope. Positive slope means it's accelerating. It's positive slope here. Here, deceleration, that's negative slope over here. And then constant velocity, the velocity is not changing. That means here you have 0 slope here. 0 slope, flat. Okay. Positive slope, negative slope, 0 slope. Okay. Accelerating, no acceleration. Constant velocity means here there's no acceleration. It's moving with the same velocity. And then here deceleration, decreasing. It's like coming to stop. Okay. So they draw the graph and they give you numbers. Sometimes they put a time here. Then they ask between which time interval is the car accelerating or the car decelerating and so on. You should be able to answer those type of questions. Okay, we'll see some shortly. Then the area under any velocity time graph gives you the distance. Okay, so I put it here. The distance traveled is the area under the graph. Okay, the area under the graph right here. What do we mean by this? So in other words, if I draw something like this, and they ask what's the area, let's say if I put a time here, a certain time, maybe 2 here, 0, so this time, velocity there. And I know this as maybe 10. And they ask you what is the distance traveled between time 0 and 2 seconds. Let's make the seconds. Okay. So the area, that's the line, and this is the interval 0 to 2, so the interval here. So the area that you're interested in will be here. That's the area. Okay, between 0 and 2 seconds, that's the area here. Okay, if you want the area between 2 to 4, then that is the area here. Yeah. And so on. And the area from 4 to whatever, then that's the area. We calculate the area here. Okay, so in other words, something like this, if I have to do the area here, then it's like this a triangle. So it's half base times height. You do half base times height here. But it's a triangle. From here to there is a triangle. So the area, which is the distance, let's say from 0 to 2 seconds, will be equal to half base, 1/2 times the base, which is 2 here, times the height here. So that's 10. So how like 10, maybe meters. If it's meters per second, then there will be meters, like that. So that's the area. If it's between, let's say, 2 to 4 seconds, distance, let's say 2 to 4 seconds. So that will be here. So the length here is, this is 4 minus 2. So that is 2 here, times and this is a triangle, right? So triangle is length times width. So the length and the width. So 2 and this is 10. So that would be like 20 meters and so on. Okay, that's how you can use the graph to calculate. But in some questions, we're going to see one question where they ask you what's the longest distance traveled or the greatest distance traveled. Okay, in that case, sometimes you don't even do any calculation. You can just estimate using the boxes, right? The boxes that is given to you. So if it's divided into maybe 1 unit, so you can use the boxes to estimate the area. So let's say that between this 2 and 4, you don't have 2 boxes. Pause between 0 and maybe 2. This like what do you call it? Maybe a 1.5 box or something, or probably like half a box and so on. You just have to estimate, so the greater distance will be between 2 and 4 and so on. You can use the boxes that's under the graph to estimate the distance. You'll see some question in the book after this, related to that. So it's not always that you have to do calculations. If they want the actual distance, then you can do the calculation that I just did, like that. Okay, right. And then some units that you should know. some units that you should know about. You should know about work done. Work is joules. Force is measured in newtons. Velocity meters per second. We measure time in seconds, right? These are the SI units, standard units for calculations. Okay. So know these units. They also ask you some of the basic units, working joules. Okay. All right, there's one question I'm going to ask you before we move on. Based on what I said about work done, assuming you have a child and myself raising a chair onto a table. So I have this table here, and you have a chair. Assuming I lift this chair from the floor and I put on this table, I have like a 3-year-old child who also comes and lifts this chair and also put it on the table, same table. Who did more work? Is it me or the child?
Would it be because they have greater distance to move it?
One person, go ahead.
So would it be the child because they would have a greater distance to move it?
Okay, you said a child.
Assuming that the child is shorter than you.
Okay, that's a good idea. Anybody?
Yeah, it's the child, because the child will have to apply more force or more energy to it by lifting the chair up onto the table.
Okay, now you're using two things. You said energy.
Yeah, the child has to apply more force.
More force.
Be able to lift the chair onto the table.
All right, you all did a good try. You did a good try. Yeah. Any other person? Let me see your thinking process. Okay, we said work done is equal to force times distance, correct? Right. Now the force is going to be the weight of the chair that we are lifting up. Right, that weight, that's a force. So the child and myself, we are all lifting the same force up, applying the same force, lifting up the same weight. Yeah. Now the distance will be the height of the table, because you're lifting this from the floor onto the table. So we are moving this through this distance here. Okay. So we do the same distance and the same work on the object, the same weight that we are lifting. So together, all of us do the same work. So same work done. That will be the answer. This is somewhere in the book. So same work done. That should be your answer. Yeah. Now, the only difference, as you said, when you use the word energy, I was happy with that, to hear energy. Now, the child put in more energy. The child used more energy than I did. That is the difference, but we did the same work. So energy is defined as the ability to do work. So the child put in more energy to do the same work. I put in less energy to do that work, same work. Okay. So take note of this question. A lot of scenarios like that too, exceptions. Okay. I'm going to ask you one other question before I talk about forces. And the question goes like this. If this is a tall building, this is the ground, I'm going to throw a ball in this direction like this, curved direction. Let's call this Y. Now the same ball, instead of throwing this, I drop it straight down. direction X. Which of these paths, or let me say, which one will hit the ground first, X or Y?
X.
Okay, somebody say X. Any other trial or thoughts? Any guess? Any other guess?
Does it depend on like the force of how you throw it?
Okay, all right, so good try. Well, the answer is they will all hit the ground at the same time. So both hit the ground at the same time. At the same time. Okay, same time. Okay, now this is what we call free falling objects, free fall. We call that a free fall, free fall. So it doesn't matter if at the same height, you throw something at the same height, whether throw straight and it curves down or you throw straight down, you know, it doesn't matter. It will all hit the ground at the same time, all right? Now the assumption here is that the wind has to be still. You don't have the wind like blowing, you know. It can be a feather. I can throw a feather, like a feather and a ball. They should hit the ground at the same time. It doesn't depend on the weight or the mass. It doesn't depend. It falls freely under the force of gravity. That's all. You know, that's what happens here. You know, you don't expect the wind. You don't want the wind to. The wind is blowing, then to be rotating the thing. You don't want all that, right? So it has to be like a still environment for this to occur. Okay, they hit the ground at the same time. So those are some of the interesting questions that you get on the tests. You know, same work done, same hit the ground at the same time, and so on. All right. Now let's look at some forces. Questions on forces. Okay. All right. Now, questions of forces are also easy to do if you know what to do. Now, the unit for force, as we said, is the Newton, N, Newton. All right. I want us to consider what I have here. The first one are forces acting on objects, right? Now we look at the in the same direction. I call them forces acting in the same direction, right? So when forces are acting in the same direction, we have something called a resultant force. When I say resultant force here means the net force, resultant, same as net force, or the sample called the effective force acting on the object, you know. So the force, you have 2 newtons acting towards the east, and they have 1 newton acting towards the east, so same direction. Now the question will be, what will be the resultant force or the net force on the object? So the net force is going to be 2 plus 1. So here you have 2 plus 1. So the net force will be 3 newtons towards the east, acting the east right here. 2 newtons east. Okay. So when forces are in the same direction, you add them up. Okay, add the forces up. That's what the key points to note here. Add them up. It's like you're helping to pull. Okay. When forces act in opposite directions, you have to subtract them. The net force subtraction, like a tug of war. So one force has to overcome the other force, and then to move the extra force that is left in the direction of the extra force. Okay, so that is opposite directions. So opposite directions, you subtract the force to the net force. So this is an example here. You have 2 newtons towards the west, and then this is acting 1 newton towards the east. So the net force will be 2 minus 1 because they're in opposite directions. So we get 1. and in which direction will be the 1 Newton? It's going to be towards the west, because you have a greater force in that direction. So the object is going to move towards the west. You know, so that's how you can get questions. Same direction, add; opposite directions, subtract them. Yeah. And then the force will be in the greater, will be in the direction of the greater one. Okay. So those are examples on resultant force. Have some examples here. Okay. Before we go on, let's look at this one, the one in the middle. Okay, so the one in the middle, if you look at this, you have 0.5 here, and this is 1. So in this direction, we have to add the forces because they're acting in the same direction. So it will be 0.1, so 0.5 plus 1. So the net force in this direction is 1.5 newtons towards the north. It's moving in that direction. Okay. Whilst the other is acting opposite direction. Now we have this acting direction, 1.5 north, 1.5 south, opposite directions. So since they're opposite directions, the net force with 1.5 minus 1.5, and that gives us a 0 newtons here. Resultant is 0. That's where it came from. Okay. So same direction, add to get a resultant, opposite directions, subtract. Okay. Okay. So these are few examples that we can practice on before we move on. Okay. So can you tell me what the first one will be? Let's call this number 1. Number 1 here. So what do you think will be the resultant force for number 1?
5 newtons.
I didn't hear you.
5 newtons.
Yeah, 5 newtons. In which direction? So 10.
They're opposite directions.
All right, so towards the west, right? In this west here, right? So 5, so it's 10 minus 5, which is 5 newtons in the west, because moving in this direction here. Okay. Okay, correct. Then let's call this one number 2. Number 2. What would that be?
30 newtons towards the east.
Okay, it's down, right? So south.
Oh.
It's going down, yeah. So
yeah.
So 10 opposite direction, so we're going to subtract.
20 south?
So 20. 30
20 newtons, yeah.
Minus 10, opposite direction to 30 minus 10, and that will be 20 newtons towards the south. It's going down here, so south direction. Okay, good. Okay, what about this one? Let's call this number 3, and we call this number 4.
That's what I meant, 30 newtons to the east.
Yeah, so 20, because same direction. This is like pushing. This is also pulling and pushing. So same direction. So it's 10 plus 20. So that is 30 newtons in this direction, which is the east. Perfect. Okay, one more, number 4.
-5 newtons to the south.
5 newtons south.
Try again. So 5 newtons south, yes. 5 newtons south. Okay. So in this direction, the same force, right, acting down. So we're going to add this. So now that we have 10 plus 2, we have 20 acting down on the object in that direction. And then this is acting up 15 newtons. So now opposite directions. So we end up with 20 minus 5, which is 5, but then it's going towards the south. That's why the larger force, the south, correct. Okay. So that's how you find resultant forces. You know, simple questions like this is what they'll give to you. All right. There's another type of question that these are special cases. I have a special case question. Now the special case question looks like this. That one let's say I have a force acting, I'll put 10 newtons here. This is acting 2 newtons down. Then another force acting this direction, that direction. Let's put like 6 newtons here. And let me put 3 newtons here. Okay. So it's acting on objects right there. So the question usually will go like this. In which direction? In which direction is the resultant force? In which direction is the resultant force? Okay.
Northeast.
Northeast. Okay.
Diagonally.
All right, let's see if what you said is correct. Okay, she said northeast. Okay, let's see. Okay. So what you do in this case, you take one direction at a time, right? One direction at a time. So in the north and south direction, use the opposite forces. So we're going to subtract. So 10 minus 2. So it means I expect it to move in this direction with a force of 10 minus 2, that's 8 newtons, right? Then the north and west south direction, or south, west east direction or east west direction. Again, opposite forces. So you have 3 minus 6. So that would be 3. Again, that will go in this direction. So it's 3 in this direction. Okay.
So
Now,
please, I have a question.
Yes.
Yeah, you said 3 minus 6, which is 3. Wouldn't it be negative 3?
Use a positive. The negative, we're talking about this big force minus the small force.
Okay.
So the effective force that's left is 3 by being the direction of the bigger force.
Force, okay. Thank you.
Just think about like tug of war.
Okay.
Who is going to win? You know, the person who wins is the one who is pulling, and that person has to overcome the 3. So the 3 out of the 6 will be neutralized. The extra 3 that is left is the pull. What the person is going to pull with.
Okay.
Something like that.
Thank you.
You're welcome. So you have 8 up north and 8 towards the west. Okay. So if something is here, you're pulling in these directions, what's going to happen? The object is like, it will move somewhere in between. The resultant force is somewhere around here, in between here, right? So for this particular answer, the direct answer will be, the resultant will be in the northeast direction. Northeast direction. Okay. That's what you can say here. You know, if you have to come with the actual numbers, you have to do more work. You know, sometimes you have to resolve forces and other things. You know, but so the test will not go into those like details. Okay? If it's like this, they'll ask you which direction. You know. Okay. All right. So I think we have enough lesson on the forces. Okay. Right. I spoke a lot about work done already. This is more detailed work done, force times distance. I spoke about that. You know, you can do positive work, you can do negative work. If the object is moving against you, you're doing negative work. You're pushing, it's pushing you. You can do positive work and so on. Okay. Or you do no work. No work means you're pushing, it doesn't go through any distance. The distance is 0. 0 times any force that you apply is 0. So no work done. It doesn't move. You know, and so on. It's all examples. Okay. No work done, positive work, and so on. Okay, great. All right, so now let's move on to a little bit of electricity, something on electricity, also one aspect of physics. Know the type of circuits that we have, you know, the wiring in electrical appliances or in the house. There are two main types of wiring. We call the first one the parallel circuit, and then the second one is called series circuit. Okay. In electricity, there are some symbols that you have to get used to when you see this. So let me write out those symbols before we look at these things here. One of them, if you see this symbol like this, don't get confused. This is how we represent what we call resistance. Okay, resistance. Resistance, anything that will oppose the flow of current, right? Current is like electrons moving within the conductor, right? Like a wire, it's a conductor. So there's opposition to the flow of the electrons. Okay, the material can oppose the flow. Some are more resistant than others. Okay. So, but this is a symbol that we use. You see the resistance. Okay. And the resistance could be like a fridge having resistance or TV having resistance and so on in it. Then if you see this symbol like this represents the battery. Okay, the long line is always the positive end, and then the shorter one is the negative end. It's a battery. Usually they don't put the plus and minus there, but you should know the long one is positive, short one is. And the current always flows from positive towards the negative. It goes from positive to negative. Okay. Another symbol, if you see this like that, round, circle around like this is a bulb. And then if you see a line like this, this is a switch. Okay. So if it's like this is an open, right? Like this is like open switch, open. If it's closed, then the lines will touch. You have a dot, then that one will touch like this. So this is a closed switch. Okay. So these are some of the symbols. I think, yeah, those are a few symbols to know about. Okay. So when you talk about parallel circuit, the parallel circuit, this is what happens. There is an alternate path to the flow of current if other paths are blocked, right? So if you look at the diagram here, if this is the current, as I said, is going to flow from positive, it's going to go in that direction. That's how the current will flow. So if I block, let's say, the path R here, the wire here is blocked. If it's blocked here, this is cut off. You notice that the current can still bypass and then flow through R and R2 and R3, and then still continue. Okay. Likewise, if I block here, I still have, we can bypass all this and then pass through. So once there's an alternate path, if one is blocked, you have what called a parallel circuit connection. Okay. If it's a series, there's only one path for the current to flow. Only one path. So when this path is blocked, there will be no flow of current, right? So if I block here, now there's no flow. Current cannot flow. It's blocked, only one path. So that is a series circuit. And there's an advantage of the parallel. Okay, if you take the wire in the house, most of them are parallel circuits, right? So you can have your fridge as R1, you can have your TV as R2, and then something else as R3. Your fridge, what do you call it? Maybe the microwave R3. So sometimes you have like maybe your TV is not working, the power supply is cut off the TV, but then your radio is working or your fridge is working, your microwaves, they are working. It's all because of parallel connection, the parallel circuits. One is blocked, they still flow through the other ones. If it's series, it means that either in series means that if one is cut off, all the power supply to everything will cut off in that particular circuit. So most house wiring follows a parallel type of circuit. These are some symbols that are used in electricity. I is for current. I for current. The unit is ampere, so know this table, the units and symbols. Resistance, we use R. R for resistance. And the unit for resistance is ohm. Ohm, I'm going to mention ohms again. Okay, ohm. Okay. So usually is a symbol here. I current is A. Okay, and the ohm, the symbol looks like this. When I write this, people ask me, is it SN2? It looks like SN2, but it's an omega symbol. Omega, like omega, that's the ohm. And then V, volts, and then watts, W, for watts. These are symbols and letters used. Okay. Power, watts. So it's a 60 watts battery, sorry, bulb, or something, or watts battery, the power that it generates or pulls. And the voltage, 20 volts, 240 volts, 110 volts, so all these things, that's what they mean. Okay. And then what's the relationship between all these things? This is very important formula as well that you should know. So the current, when I say current, let's go to voltage. When I say voltage, the voltage across any circuit is calculated by multiplying the current, which is I, times the resistance. V is equal to IR. V is equal to IR. Okay. Very key to working some problems in the book. So keep this in mind. V is IR. Okay. And this is what we call the Ohm's law. This is referred to the Ohm's law. Okay. Ohm's found that the voltage is proportional to the resistance, or the voltage is proportional to the current. In other words, as the current goes up for the same resistance, the voltage also increases. If the resistance increases for a particular current, the voltage will also increase and so on. Same direction of change, proportional. Okay. But when you take the current and the resistance, for any particular voltage, as the current goes up, the resistance goes down. Resistance down, current up, like inverse between current and the resistance. Okay. Okay. So that's Ohm's law. So when I ask you what's Ohm's law, you should to state is V is equal to IR. Okay. Voltage is proportional to the current or the resistance. Okay. And then the other formula is the power. The power formula that you have here, power. The power, if you can remember, is voltage times the current, VI. That is power. Voltage times current, VI, that's power. Okay. So the other one here, you can generate that easily. If you know these two, you can play around with many questions. Okay. I'm going to do something here. Now, let me replace the V. I'm going to replace the V by IR. So I'm going to put IR here. The V, because V is IR. So let's put IR. Because that's the V from number one. Times I. Okay. What do we notice here? We end up with P is equal to I times I is I squared. And then the R. So this is where the second formula here comes from. What you have here, this is where it comes from. By replacing V with IR, I can get this formula here. So these are two formulas that can be used to calculate power. P is equal to VI or you can say P is equal to I squared R. Depends on what is given to you. If you know I and you know R, you can calculate power. If you know I and know V, you can calculate power, and so on. You can play around with these formulas in questions. Okay. All right. Any question on the electricity? The first part. So a lot of physics today. Yeah. So now you do very well on the test. Okay? I know some people take the test without going through physics. So if you, what you know is now going to be good for you. It's going to help you a lot. Okay, so I believe you're okay so far until we start applying to questions, right, later. Okay. Okay, now let's look at the other part, electromagnetism. Electromagnetism. That's also an interesting topic. Okay. So let's begin by looking at what a magnet is. Magnet. So electromagnetism, magnetism, there's a magnetic field around a magnet. So if you take a magnet, you have what we call the magnetic field around it. So every magnet, let's say, have this as a magnet. Okay. There's a field, an area around the magnet where you feel the force. And that's what we call the magnetic field. Okay. And usually you represent this by what we call the magnetic field lines. I'm going to draw that for you to see. Right? Every magnet has what we call a north pole. It has the south pole, north and south poles. Okay. Now, when you suspend a magnet on a rope or a thread, it's going to move around, spin around, and then to align or orient itself in the north and the south direction of the earth. You know, that's how we come across the north and south poles, you know, because it always will spin to a line in that direction. And that's the very reason why they use magnets in the compass, you know. So no matter any direction you turn, it's going to turn around and show you the north and south directions, you know. That's for a magnet. Okay. So the field lines move always, they move from the north into the south. All right, so it goes like this. Then you point the arrow from like this, north, and then moves into the south. North to south. Arrow in that direction. It moves from the north to the south. Moves out of the north into the south. Enters the north, enters the south. Right? So if you see it in a diagram, you should be able to know, determine whether it's a correct drawing or wrong drawing. You know, they can draw for you and put the arrows in the wrong direction. And they should be able to tell it's wrong. All right. Okay. Always the magnetic field lines, they move from the north, out of the north and enter the south. It should be like this all the time. All the time. Okay. So those are the field lines, magnetic field lines. That's what I've drawn. Okay. And this experiment can be done in the lab. You know, if you get a chance, you can Google maybe field lines and see. They put compasses along this path, and then it shows the direction in which the force are moving. Very beautiful diagram. This ion filing. You put ion filing on the, like a paper. You take a paper, put a magnet under it, and then put like powdered ion on it. It gives a nice pattern, like what I've drawn here. You can Google the diagram, and you see the beautiful lines of the ion filings on those lines like that. Okay, so know this diagram very well. North pole, south pole, and then the field lines goes like that. Okay. So with this knowledge, we can draw various diagrams of how magnets attract each other or repel each other. Okay. All right. So we always say that when you have like poles of a magnet, they always repel, and the unlike poles always attract. All right. So North Pole will attract South Pole, while South Pole would repel South Pole, or North Pole repel North Pole. Okay. Unlike forces attract, same forces repel, move each other apart. Okay. The magnets. And to draw the magnetic field lines, before I even go there, these are some properties of magnetic lines of force, which I'd like to read through. The magnetic lines of force originate from the North Pole of the magnet and end the South Pole. Very important. The magnetic lines of force come closer to one another near the poles of the magnet, but they are widely separated at other places. In other words, as they get closer pole, they get closer and closer together. But here, like they get wide, they are widened in wide space in between, like here, and they get closer. Okay. Now the magnetic lines of force do not intersect, so they don't cross each other. So I can't draw this without crossing, like over here. No, they don't cross each other or intersect each other. So when a compass is placed at different points on the magnetic line of force, it aligns itself along the tangent to the line of force at that point. Okay. So if you place compass here, it's aligned itself. Let's say that the compass would align in that tangential tangent. So that's how they come up with these lines. Or because the compass that they place on at different points, and they draw the lines out. Okay. All right. So this is a diagram of the magnetic field lines. I just drew that. That's how it looks like. No, just showed you already. So let's look at the interaction, how they interact. If you bring a north and south pole together, what happens? They attract. So this is north and south. Okay, see the lines of force around the north, they join together. Okay, they join together over here. Okay, so as I said, if you forget, you can always draw it yourself. If I bring, let's say, north and south together, what will happen? We said the north will always, the field lines move from the north into the south like this. North into the south, north into the south. So that's how the diagram looks like. You know, they attract like this. Okay. So you want to draw the other side, that means that this is your north here and south there. Okay. Then you have all this here. It moves out of the north, you know, moves north to south, like over here, they're gonna have to like south. You know, that's how the diagram, you know, then moves out. Do the arrows correctly. Yes. So if you draw so many of them, then you get this diagram that you have here. You know, same thing here. North to south, like. Important correct arrow direction. If you take the north and north pole, or the south and south pole, if you bring them together, it's going to repel. So north, south here, and then maybe another south, north. So let's draw in between what happens here. The force comes in north and goes to the south, north to south, another north to south, goes in like that. Moves out. And then here it comes in here. But then they will never meet. They will not intersect, okay? Because they repel each other. So you're gonna have all this coming in, but no intersection, okay? So that's the repulsion. They repel each other. That's what you see here, the repulsion. over here. Okay. If you do north and north, the same thing will happen. So same thing. Yeah. So know this diagram. When they draw, you know attraction and repulsion over here like that. Okay. Right. Now with this knowledge of magnets, we can now talk about what we call electromagnets. So let's talk electromagnetism. All right. So electromagnetism is a study that involves the use of electricity to create magnets and vice versa. That is, using a magnet to generate electricity. Okay. That's what we call electromagnetism. Electromagnetism. Magnet to create electricity or electricity to create magnets. Okay. So electromagnetism describes the relationship between electricity and magnetism. The electromagnetism works on the principle that an electric current through a wire generates a magnetic field. When you wrap a wire around a metal object and pass a current through the wire, that object becomes magnetized or becomes an electromagnet. Likewise, when you move the magnet within a coiled wire, it generates current or electricity. Okay, this is a very simple experiment that you can do yourself, or if you have kids in school science projects, they can easily do. You take a wire, copper wire, and then you can roll into a coil. You form a coil out of it, like that. And then let's connect this to, let's say, a battery over here, like this. So that's a battery. And then you put an what do you call an iron rod here inside the coil. So this a rod, iron rod. Okay. And this is copper wire. It's a battery. Now this setup here, the coil that you form here, this coil here, where here is the setup here is what we call a solenoid. Solenoid. That's the coiled wire, solenoid. Okay. If you pass electricity through this, what's going to happen? You will notice that the iron rod here will become magnetized. The iron rod becomes magnetized. Becomes a magnet. Iron rod becomes a magnet. Okay. All right, that's what happens. Becomes a magnet. So they apply this a lot. Application, let's say at the harbor. If the harbor, usually if you watch TV, you can see all those big, what do you call it, containers, large containers. They have these cranes. They have a metal that's they used to pick up the containers. They pass current through the metal, and then once they pass current through that round metals, it becomes magnets that can. They're strong, powerful magnets that can be used to pick up the containers. So that's one application at the harbor. So it gets magnetized. Now the opposite can also occur. The opposite, if I take again a solenoid, but this time I put a bulb. So put a bulb here. So remember symbol for a bulb. So you put a bulb here. And then you put a magnet. This time we have a magnet here. This is a magnet. Okay. If you move the magnet in and out, you have to move this magnet in and out of the coil. Move it in and out. You're going to realize that current will flow. Here, current will flow. And then what's going to happen? The bulb lights up. Okay. You don't need battery here. Bulb lights up. Very simple. Okay. And one application is in a bicycle. The bicycle, they have a solenoid like that, an arrangement like that there. As the person paddles, the person is rotating or moving a magnet in the coil, in the solenoid, right? And as the person paddles. So as the magnet moves in the coil, it creates electrical current. So the current flows through the bulb, and then you see that the bicycle bulb lights up. Anytime the person paddles, it lights up. Paddles, lights up. Okay, if you stop paddling, then it goes off. That's a very simple setup in the bicycle application. And then not some few years ago, I don't see it on the TV these days, but they used to advertise a dot. Somebody created has a torchlight. It says you don't need batteries. You know, they have a solenoid in there. So what have you shake it, and then you can light. Anytime you need it, you just shake it, you click, and then lights up. It's all simple arrangements put in the what do you call it? The torchlight. Okay. I think I went somewhere recently and I saw another one where that one is like a lamp, like a lantern, but you crank it, you rotate, you use your hand to rotate, you know, one of the wheels, and as you rotate it, it charges and lights up. You know, it's the same setup. You know, people are making money out of it. You know, very simple setup. It's called a solenoid. Okay, so that is what electromagnet is all about. Okay, so let's read this here. Say, what is a solenoid? A solenoid is a long coil containing a large number of closed ends of insulated copper wire, right? So it's insulated. A magnetic field is produced by the current carrying solenoid. The strength of the magnetic field produced by the current carrying solenoid is directly proportional to the number of turns and the strength of the solenoid. So it means the more turns that you have in the coil, the more coils, the stronger what do you call the stronger current that you can generate, right? It is also dependent on the nature of the core material. So depending on the material that you use, the iron, is it copper wire, and so on. It also affects the strength. So when soft iron rods are used as cores, they produce the strongest magnetism. So soft iron produce strongest magnetism. Solenoids are used for making electromagnets. Okay, so what's electromagnet? We said all that already. When electrical current flows through the soft iron rod placed in a solenoid, a temporary magnet is created. It acts as a magnet only so long as the current is flowing in the solenoid. This combination of a solenoid and soft iron core is called electromagnet. Electromagnet therefore consists of a long coil of insulated copper wire wound on a soft iron core. And these are some uses of electromagnets, right? Used in cranes to lift heavy metals. I said that already at the harbor. Used in electrical bells. Electrical bells, you have that in there too. Radio speakers, microphones, dynamos. You can use to generate electricity. Store memory in computers. Pictures on the TV screen and so on. Diagnosis like MRI. You see all these things there. And then this is a setup I just described. You know, you can take like a nail coil battery, it becomes a magnet. You can attract metal. And then this is the same setup, right? Where it's another diagram of it. All right. So those are some of the things I'd like to talk about on the magnet. Any questions so far on the magnets? Any questions so far? So we are fine for now. Okay, great. All right, so I think that will end our physics part for today. If any other thing comes up, I'll talk about it. But for now, I think that's a good overview of the physics. Okay. All right, we're getting there slowly. Okay. I'm going to shift our brains again back to some chemistry. Back to some chemistry. Okay. So let's talk about something new here. We want to talk about organic chemistry and how to classify organic compounds. All right. Sometimes they ask you, they give you some formulas, and they ask you to identify what class of compound it belongs to, which group in organic chemistry. I know some people have done it, some people have done organic chemistry, but even if you've not done it, you should understand what I'm going to talk about today, classification. Now, organic chemistry deals with carbon compounds, and hydrogen will be part of it. Carbon compounds and hydrogen attached to them. You may have other things like oxygen, sulfur, phosphate, and hydrogen, and phosphates, nitrogen, and attached to them as well. But in general, we're talking about carbon compounds, carbon compounds with hydrogen somewhere. Okay, that's a general thing. And the groups that we have are one, they are called alkane. Alkane. Okay, when I say alkane, you're talking about single carbon to carbon bonds. Single carbon to carbon bonds, alkane. Okay, this is what I mean. Now, carbon always has four things around it, always four things. So if I have CH4, we call this the condensed structure. We can draw the expanded, the structural formula for it. The structure with carbon and there are four hydrogens, like this. This is an example of an alkane, single bonds. Like, let me draw this here first. We have, let's say C2, C2H6. You have this formula. The structure is going to look like two carbons, so to be C1, 2, and they have hydrogens around it. Okay, so this is C2H6, right? Because I have just one bond between the carbon, it's an alkane, single carbon to carbon bonds right here. What do you have? Okay, alkane. We can keep drawing more structures. Okay. Now, the formula, if they give you any compound, the general or simple formula that I can use to identify alkanes is this. The relation between hydrogen and the carbon. If you look at this, this is, let's call this N. N. Now, the number of hydrogens is always going to be 2 times the number of carbons plus 2. This is a good formula that I would like you to keep somewhere. 2 times the number of hydrogens plus 2 gives you, sorry, 2 times the number of carbons plus 2 gives you the formula for an alkane. Okay. So when I give you a question formula, you look at it. This is 2 and 6. Is it 2 times this plus 2? They know the alkane. Okay. Because you're not going to have time to draw all this on an exam. As if I give you something like 20 and I write this and I tell you which group of compound does it belong to. You're not going to have time to draw out everything. There's no time for that. So all that you do, you look at the numbers, the carbon, and then the hydrogen, the numbers. Okay, is 42 made up of 2 times the number of carbons plus 2? Let's see. 2 times 20 plus 2. What would that give me? It gives me 42. So once this is true, okay, 2n plus 2 for the hydrogens, then you know that you are dealing with an alkane. So this is an alkane. Okay. 2 times this plus 2. Okay. And we describe it as they are saturated bonds. Single bonds, they are saturated. You know, you can't add anything to it. Remember, carbon always has 4 things around it, right? It has 4 bonds or 4 arms, always for carbon to make it stable. So that's an alkene. Now, what about alkene? An alkene, the second one, alkene, E-N-E. An alkene has double bonds in it, double bond, alkene. So I'm going to draw that for you to see. So alkene, alkenes. Okay. And the example that I'm going to use, I'm going to write C2H4. C2H4. Now, expanded structure for this will look like carbon, carbon, then you have 4 hydrogens. So 1, 2, I can put 1 here, another 1 there. But then carbon is happy, carbon is 4 things. So it means there's a double bond here. So the bond 1, 2, 3, 4, 1, 2, 3, 4, 4 arms or 4 bonds around carbon all the time. Okay. So you see you have a double bond here. Double bond between carbon and carbon. Once you see that, you are doing for the alkene, E-N-E, alkene, double bond. Okay. Somewhere. So what is a general rule? The general rule, I'm going to put in a box. If you look at the relation between hydrogen and carbons, it's always going to be CnH2n. The hydrogen is always going to 2 times the number of carbons. Okay, 2 times always. So they give me something like C20H40. I know that it's an alkene because the hydrogen here is 2 times 20. That gives me this. Okay, twice. I know it's dealing with an alkene. So I don't have to draw all the structures out. There's no time to draw everything out. Okay. Then the next one is an alkyne. Alkyne. A-L-K-Y-N-E, alkyne. Alkynes have triple bonds between the carbons, triple, 3 carbon bonds. Okay. So they are unsaturated, means other things can be added to the bonds, can break the bonds and add things to them. So alkyne. Alkyne. So alkynes, example C2H2. That's a basic structure for one of them. So C1, 2, you're gonna have triple bond and then hydrogen somewhere like that. So once you have triple, see this anywhere, you have an alkyne. And the formula that you can use to identify it is CnH2n minus 2. It's 2 less than twice. The hydrogen is 2 less than twice the number of carbons. 2 less than twice the number of carbons. So they give you a big formula, C20 times 2 plus minus 2, so 38, like this. Compare. So this is 2 times 20 is 40 minus 2. That gives you 38, which you have here. So it means that this is an alkyne. You know, you check like that and you can tell us alkyne, alkane. Okay. So if you look at this, alkene is in the middle. Alkane is in the middle, right? It's 2N. If you add 2 to it, you get an alkane. If you subtract 2 from it, you get an alkyne. That's how you can remember it. Yeah. 2 extra hydrogens or 2 less hydrogens. So please look at this one carefully so that we can use that to identify the groups. Okay. Any question on what I just did before we look at other groups? Okay. All right. So the other groups that we're going to look at, another group is alcohol, the alcohol group. Okay. Now the alcohol group, if you look here, I'm using R. I'll explain what the R represents. R represents what we call the alkyl groups. The alkyl groups. Alkyl groups are like CH3, you know, and CH2. I mean, they are alkanes that have one less hydrogen. You know, one less hydrogen. Then we call them alkyl groups. Okay, so if you see R, it means a group of CH3 compounds. You know, the alkanes with one less hydrogen. So it's like CN H2N plus 1. That's how they look like, plus 1. Okay, R group. So let's do alcohols. Alcohol. So the alcohol group, example would be, let's say have C, let me put OH here, hydrogen around it like this. Okay, so what we have here, the formula will look like this: 1, 2, 3. So sorry, 2 carbons. How many hydrogens? 1, 2, 3, 4, 5. So H5, and then the OH here, OH. So that's the formula for this alcohol, this ethanol. Okay, this ethanol, alcohol, ethanol. That's how it looks like. Okay. So the R group that you're referring to, this R group, everything here is the R group. That is R group. So if you come here, this is the R group you're talking about, R group. Okay. That's why we put in the alcohol formula as ROH. Okay, because this part can change. I can have 1 carbon, I can have 2 carbons, 3 carbons. The R can change. So all this is the R group. Okay, R group. The yellow one's the R group. Or the alkyl group. Okay. So anything that you see CH, something like you see OH attached to carbon group, they know you're dealing with alcohol. Okay. This is another example, CH3OH, alcohol. So here, that's an alcohol. So this is our group here, right? COH, alcohol. Then the other one is called carboxylic acid. Carboxylic acid, you have an R group, and then the COOH, according to the cool group. If you see the cool group attached to R, then you are dealing with a carboxylic acid. Carboxylic acid. Okay. The other one, so this is an example, right? They have esters. If an ester is you have an R group and an R group, but in between you have COO. So you have COO holding on to our group. So look here, like CA3, COO, and then another R group, R, COO, R. They are doing work on an ester. An ester is formed between alcohol and the carboxylic acid. When I say an ester, I'm going to write that somewhere. Well, I have it here. Ester is formed when an alcohol reacts with a carboxylic group. You have an ester. This process is known as esterification. So when I ask about esterification, is a reaction between alcohol and carboxylic group, ester. And esters, they smell real good. In its sweet, they have sweet smell or sweet scents. Like the nail varnish is an ester, alcohol with carboxylic acid. Nectar is, they're all esters. They have very fine and what we call it, sweet scents. They're all esters. Alcohol mixed with reacted with carboxylic acid. Okay. So it should be identify esters.
I didn't understand, so I don't know where I walked and they got wet.
Someone has a question? Yeah. Okay. All right. Then the other one is aldehyde. Aldehyde. I think I left the A. I left L here. It's al. Aldehyde. So there should be L over here. Aldehyde. L here. Okay. Aldehyde. So for aldehyde, you have an R group with at the end you have CHO, right? CHO, aldehyde. So R group by CHO, you have aldehyde. So if I break it down, an aldehyde will look like this. Aldehyde. Anything that looks like you have C and then you have double bond oxygen, and then you have like H here. H. And then you have an R group here. Okay, so this is a CHO end. This end is the CHO. Or R attached to CHO. That's the CHO. If I condense it, that's what this is. Aldehyde. Okay. And as example is what I have here, CH3, CHO. Okay, that's an example. They have a ketone. Ketone, you have R group with CO in the middle, and then another R group. So CH3, CO, So what I have here, this here can be written as, if I want to draw everything out, it's like having CH3, they have the carbon, and they have double bond on it, and then another CH3. This is how it will look like. So in other words, the hydrogen here in the aldehyde is replaced by another R group. If you replace it by another R group, then you have what you call the ketone, right? So ketone group looks like R. They have the double bond on, and then you have another R here. The prime means it can be the same or different R, like a prime. When we use prime, just to distinguish the two R's. Okay, same or can be different. So it's like two R groups being held by CO. You have a ketone. Okay, and then the last one is known as ether or the ethers. The ether, you have R group held on by two R groups held together by oxygen in the middle. So this is the ether. Example is CH3, O, and CH. Two R groups held on by oxygen. Then you have what you call the ether. Okay. So you should be able to identify different groups of compounds under organic chemistry when you're given those things. Okay. So based on what you've done so far, let me do a quick quiz, a quick one. Let's see. Let me ask you some quick questions. I want you to tell me which group each of these will belong. So the first one, classify them. One, C30H. Two, C30H. 58, C20, then let's make it 22, H44, 4, C3H7, COOH, 5, CH3COO, CH2H5, 6, CH3O, C2H5. Okay, there's some few ones here. Which group would you classify the first one to be? Number one.
Alkane with the A.
Alkane, correct. Because this is 2 times 30 is 60 plus 2, right? So this is alkane, correct. Okay, the next one.
Alkene with the E.
Alkene with the E, perfect. Wait, no, hold on, let's see. Times 2 is
Sorry.
60.
Sorry, it's alkyne. Alkyne with the Y.
Alkyne, yeah, alkyne. Because times 2 minus 2. Alkyne Y. Triple bond. Okay. And then this one will be
Alkene with the E.
alkene with an E, correct? And then this one, the cool group, carboxylic acid, right? Carboxylic, because COO at the end. So it's a carboxylic group, carboxylic acid group. Okay, this one. So you're looking at this here. You have COO holding on to 2R group. It's an ether.
It's an ether. Oh.
Ether, it's an ester, rather, not it's
Ester.
Ester. It's an ester. It's an alcohol and what do you call it? Carboxylic acid when it reacts. So that's an ester. Okay. So this is going to smell good, like perfume, perfume, alcohol, and carboxylic acid. And then this one will be oxygen holding on to our 2R groups. That will be the ether. Okay, oxygen holding on to our groups. Ether. Okay. So when I give you those compounds at least, you should be able to apply this knowledge to the problems. Okay. Right. Any questions? I hope everybody understands what I've done so far. Okay. Everybody's good? Identifying the compounds. All right, so silent means everybody's fine. Okay, right. So we have another section to talk about here. Metabolism, okay.
Professor?
Yes, please.
Hi. So just want to let you know the attachment you sent in the meeting, like from the Google Classroom.
Yeah.
The stuff are readable, like the images are readable from like first couple of pages, and then towards the end, there's nothing in it.
Oh yeah?
Yes, they're all like exclamation, unless it's just me, But like I tried to use my Google Chrome and then a PC and then another one. It's nothing is showing up on a like probably page 1 to 3 is good, but then
Yeah.
towards the end there's no more. They're all just like bunch of exclamation points.
Oh wow. And did anybody have the same problem?
Yeah, I did also.
Yes.
Because I see, because it's the same one that I posted, like the one that I'm also having, that I'm showing on the screen. It's the same one. Okay, I'll try and post again and see.
I think it's just the images, but then the word portion of it, like the letters, the text is okay.
Yeah.
It's just the images.
Oh wow. I don't know what is happening then. Because mine too, there's a little shift in the arrows and all those stuff. So I have to go back and see what. I'll check and maybe repost again, probably.
Okay, thank you, Professor.
Yeah, thank you for letting me. Okay. All right, so far we're almost getting to the end of the science portion here. I think we're on track. We are on track here, okay, yes. Okay, right, so let's look at metabolism. That will be quick because we know most of them already. So remember, metabolism is a process by which organisms build up or break down substances. It consists of anabolism and catabolism, right? And anabolism is the synthesis of complex substances. And synthesis is the production of more complex substances by combining two or more simpler substances, right? So you're forming synthesis, for simple to complex, right? Something like glucose to glycogen, that is an example of anabolism, okay? You're building up something. Glucose is simple, becomes complex glycogen. And then catabolism, now you're breaking down. So you're breaking down complex substances into simpler ones, like breaking down glycogen to glucose is an example of catabolism, right? So if we come to some examples of anabolism would be photosynthesis in plants. It's an example of like anabolism. You're building up, right? And then respiration would be an example of catabolism. So you're going to break down. So this diagram just shows you the relationship between like photosynthesis and respiration, what happens, and then we're going to see that shortly. We live in harmony with the plants. Okay. So let's begin by looking at photosynthesis. You have to know photosynthesis, the general formula, general equation for photosynthesis and respiration also very, very well, okay? Or sometimes they give you the equations to identify. So I'm going to talk about that now. So remember that photosynthesis occurs in plants and you need these things. So let's look at photosynthesis. Photosynthesis. I mean, it's very complex, but we'll look at a general overview of it. Okay. Usually it has what we call light dependent and independent parts. But for the test, you don't need those details that are involved here. You just have to know the fact that it occurs in plants and you need carbon dioxide, CO2. You need carbon dioxide from the atmosphere. And then you need water, H2O, right? You need water from the soil or from the atmosphere, wherever it comes from. You need some water. And you need sunlight, very important. Sunlight is needed. Energy from the sunlight. So there's no energy from sunlight, photosynthesis will not occur. And then you need chlorophyll. Chlorophyll. That's a green pigment or coloring substance in the plant. Chlorophyll traps the sunlight. Okay, that's where the energy, a light and dependent thing comes in. Chlorophyll. And then once all these are present, then you form your glucose, which is C6, know the formula for glucose, C6H12O6. So this is glucose. That's the product that is formed. And then you have oxygen, O2, that is given off. Oxygen becomes like a waste product in photosynthesis. So O2 is given off. So carbon dioxide, water, and sunlight, chlorophyll. So know this formula very well. So this equation. Okay. If you balance this, then we're going to have 6 written in front of carbon, and then this will be 6 here. And then oxygen O2, we have also 6 here. Then it's balanced. So C6 CO2, 6 molecules of water combine to produce 1 molecule of glucose plus 6 molecules of oxygen. Okay. This formula, since this equation is very, very important to remember, very important, I'll put asterisk on it. Remember that. You see that, that is photosynthesis. Once you know this, you know respiration. The formula for the equation for respiration is just backwards. You're going to see it's backwards, you know. So when you go to respiration, you just turn this backwards and then you have respiration. So respiration will be, now you take glucose, the sugar. What do we need? We need oxygen. And it combines the oxygen, and then the end product will be, you have carbon dioxide, waste, plus water, that is waste. And then we produce energy in the form of ATP. So this will give us plus ATP, energy. That is respiration equation. If you balance this, they have your 6 here, 6 there, and a 6 there. Now, the ATP can be 38, it can be 34, and so on. No, 36, you know, like if a human, you know, sometimes 38, sometimes 36. So that can change here. But this is a general equation. So note those 2 equations. If you know one of them, turn backwards, the other one. Okay. So what's happening here is that oxygen is a waste product in photosynthesis. When it comes to respiration, we need oxygen. So the plants produce oxygen, which we take for our respiration. Then we give our carbon dioxide, and the plants, they take up carbon dioxide. You know, so it's a cycle. It's a nice cycle. That's why you have this cycle here, the relationship between the two. You know, waste becomes the useful product for the other one, and so on. Okay. Now, I want you to note the fact that respiration that we talk about is not just breathing in and out. You know, that's not the respiration. We're talking about internal respiration here, cellular respiration, and cellular respiration is made up of 3 parts that you can see here. The first part is known as glycolysis. Breaking the glycolysis is the first part, you know, where you break down the glucose, you know, into what we call pyruvate. It's a series of processes that you go through. You do more details of that in your biochemistry classes of physiology classes. So it goes through the process called glycolysis. And at the end of glycolysis, you produce 2 pyruvates, you know. Now, depending on whether it's oxygen present or not, the pyruvate will go through either fermentation to produce alcohol or lactic acid if it's in the muscle, you know. If there's oxygen present, then it goes through what's called the Krebs cycle. So Krebs cycle is the second stage in respiration. if there's oxygen present. Now, within this cycle, you produce what we call reducing substances. You come across NADH, this one, and then you have what we call FADH. They also they're called the reducing substances. Those reduced substances go through the last step called the electron transport chain. And the electron transport chain, that's where you produce a lot of your ATPs. So about 38 ATPs will be produced in the energy production, mostly producing the electron transport chain. Okay. Okay. All right. Now, during glycolysis usually you produce about 4 ATPs, but you use up 2 in activating the glucose. So at the end of glycolysis, you only have like a net of 2 ATPs being produced, right? But most of the ATPs are produced in electron transport chain. So that's what happens if the electron transport chain is poisoned. Then you have a problem. That's why some of the what they call lethal injection that they give ends up blocking the electron transport chain, and that makes the person cannot produce ATP, and the person ends up dying. No. Okay, so that is an overview of respiration. So remember the steps. Glycolysis, breaking down glucose through a series of steps to produce pyruvate, right? So many steps here, very detailed steps. But we don't need all that for the test. Then after the glycolysis, you have Krebs cycle, also known as the citric acid cycle. You produce pyruvate. Pyruvate is changed to what we call acetyl-CoA, which then combines with other chemical substances in the cycle to produce what we call the reducing substances, NADH, FADH, as I said. Okay. Then the electron transport chain. In the presence of oxygen, NADH and FADH, they pass through the electron transport chain. It's a chain of enzymes that generates ATP. So this is where most of the ATPs are produced, as I said. Okay. And then the formula. And that formula, and I asked them, what happens if there's no oxygen? I explained that already. There's no oxygen, pyruvate is changed to what we call lactic acid, right? This is what causes the muscle cramps when you run over a long distance. Muscle cramps for a long distance. Okay. Yeah. Then you have fermentation. The fermentation can occur if there's in the absence of oxygen. It's an anaerobic process. So the pyruvate can be changed to alcohol. Can change the alcohol if there's no oxygen. Okay. And then we spoke about photosynthesis, all that I explained. These are all the formalized equation is here. So please take note of that. Okay, good. So this is a good point. One last part here, then we can pause a little bit. Okay, so the last point I want to make here is what we call tropism. Tropism in plants. Now, tropism in plants refers to the movement or response to plant parts to external stimuli. Just as somebody touches you, we respond to it. Plants also have their own response to environment as well. So a tropism is a biological phenomenon indicating growth or turning movement of a biological organism, usually a plant, in response to an external stimulus, right? In response to external stimulus, or the responses of plants to the environment, or a plant's directional growth response to a physical stimulus. So it has a response. How do they respond? There are different types. It's easy to remember the types. You just have to look at the name and then you know what it means, and even if you forget. So you have phototropism. Phototropism, when you have a plant, it always grows towards light. Okay, so some of the questions, so they draw a box like that, they put a plant in here, and then they'll do something like this, like it's growing, and they have sunlight there. And they ask which of the following is describe the response of the plants, in this situation. So there's phototropism, response to light. It's a plant growth response to light. Response to light. That is phototropism. Okay, so the growth of the stem and leaves towards light. Then you have geotropism. Geotropism, that refers to the growth of the roots towards the ground. Okay, so if you have the roots, if you put on the side somewhere like the soil, you see that the roots always grow towards the ground. That's known as geotropism, growth towards the ground. And then you have for gravitropism. Gravitropism, growth response to gravity. The plant roots grow down with gravity. The shoots or the stem grow up against gravity, okay, and out of the soil. Okay, those are gravitropism. I have phygmotropism. Phygmotropism means plant response to touch. Okay, so growth response to touch. There are some plants when you touch them, they close. They can trap flies and so on. Touch it closes. Or those that are the vine, like they grow around stick or can climb walls, they touch and then they end up growing. Those are response to touch. They grow around the tree. Okay, like the vine grows up around trees. The Venus flytrap closes when the leaves are touched. Those are all examples of phygmotropism. They have chemotropism, growth towards like chemicals. Hydrotropism, it means growth towards water. So the roots grows towards water, And all these responses are due to plant hormones, the growth hormone in plants that is called auxin. Auxin controls these type of responses. Like sunlight, if sunlight shines on one side of the plant, the auxin move to the opposite side of the plant, like the side away from the light, and then they stimulate growth on that side. So that side grows faster and the plant and bending. So all the responses are due to the hormone, the auxin in plant growth hormone called auxin. Okay. So this one summarizes the different types of responses, okay, in the diagram form. Okay. So once they give you just look at the name and then you can remember. The other thing that they add to this is they say positive tropism, positive or negative, right? They say maybe positive phototropism, or negative phototropism, and so on. So when they say they add a negative and plus, plus means towards. Negative means like away, right? Favorable response, unfavorable response, towards and away. That's what the plus and negative will mean. So, okay, right. So I think that should be the end for this one. You know about homeostasis already. The body's ability to keep a normal internal environment, right? Homeostasis, I believe you know that one already. So it's cold, your body, you shiver to generate heat, to warm up. If it's too hot, your body tries to cool itself down by you sweating and so on. Okay, that's homeostasis. All right, so this is a good point to end for today on the science so that we can look at the book and answer some questions, on all that we've done today. Okay. Any questions before we hit the book? We'll take like a few minutes break and then we'll come back. Any questions before we go for a few minutes?
No.
So far, so good. Okay. Right. So let's take I think 5 minutes break will be fine with us. Just stretch our legs a little bit, drink something. So let's go at like 5 minutes. So it's 12:10. Let's make 12:05. Stretch a little bit. And then when we come back, we would look at some questions from the book, and I'll highlight data analysis as we go on. And after that, we'll look at the math. Okay. All right, so let's take a break now. Okay. I'll go through the questions like we did last time. I'll mention the page and then we'll look at it. Okay. Okay, look at page 221. Page 221. Number 22. It says, which of the following equations represent neutralization reaction? Which one represents neutralization reaction? And then they gave you different equations.
I'm sorry, what page was it?
Page 221. 221. Number 22.
Is it D?
D?
D.
Yeah, it's D, correct. D. So you see, if you look at D, you have acid, you have a base, and then water and salt. Okay. You have H. So 22, you have H, 2CO3 plus CaOH, 2 of this, plus giving you so this gives you 2H2O plus CaCO3 like this. Okay, so that's your acid. You have this is a base OH, and then this is the water, and that's the salt. So that makes it neutralization, correct. All right. Let's look at number 14. I want to talk about number 14, something that came to my mind. I have to talk about that now. So look at page 220, number 14. 220, number 14. Okay. Okay, it says a ball rolls down an incline, passing through the 4 positions shown in the diagram. In which of these positions that the ball have the maximum kinetic energy? Okay. I didn't talk about the kinetic energy yet, so I'll use this to illustrate and talk about that. So you have A, B, C, and D. Okay. Let's rolling down. Okay. So let's talk a little bit about kinetic energy, the type of energies. Energy. Okay. So many different types of energies, but I want to focus on one, what we call the potential energy. Potential energy. And then the second one will be kinetic energy. Those are the 2 types of energy I want to talk about for now. You can have thermal energy, electrical energy, and so on. But we'll talk about these 2. Now, potential energy is the energy that an object has by virtue of its position. So energy due to position. Energy due to the position of the object. They would call that potential energy, right? And this is found by the potential energy, just called the E. It's found by multiplying the mass times gravity times the height. Mass times gravity times height, mgh, all right? The height of the object. H is for height. Okay. So this is height. Force kinetic energy is the energy due to motion. When an object is moving, it has kinetic energy. So energy due to motion. Okay. So the object is not moving, it has no kinetic energy. If the object doesn't have any height, it has no potential energy and so on, right? So one way we can look at this is to use the diagram that we have here, right? So if an object is, let's go back to the diagram here. So this is the ground level, right? Ground level. So when the objects are high up here, because it's above the ground, it has potential energy. So A, for example, has potential energy if it starts here. It has potential energy here. So I'm just going to use PE for potential energy, right? PE. It has potential energy here, PE. So let's use PE for potential energy and KE for kinetic here, KE, PE. Okay. So once it starts moving, it has both kinetic and potential energy. Remember, potential energy can be changed from one form to another, right? We can't destroy, but change from one form to another. So the energy here, potential energy here, will be changed to kinetic energy. So in between, you have both. The total energy will be both potential energy and kinetic energy, right? In between. When it gets to a ground level, because there's no height, all the potential energy is changed to kinetic energy here. So here you have kinetic energy, maximum, ground level. Here we have maximum potential energy here. Kinetic energy here will be 0. KE at that point is 0. Once you get to the ground level, there's no height, so 0. H is 0. So the whole of PE here is 0 at that level. Okay. Now D is above the ground. So it's going to have, again, this D here is going to have both potential and kinetic energy at that level. Okay. So this summarizes the different positions. You can have the same thing with the pendulum. If you take the pendulum, it's very similar. The pendulum is swinging. This is a starting position. If it goes there, because this is the original position. So if you move it here, you displace it. So there's a height over here. So over here, it has maximum PE at that point. Kinetic energy at that point will be 0. As it drops down, the kinetic energy will be changed to, the potential energy here will change to kinetic energy, right? So once it gets here, the height above the original position is 0. So to have the maximum kinetic energy will be here. And then the potential energy at this level is 0 because there's no height, something displaced. And then the whole thing repeats itself. It goes here, maximum height, because that's the height here. So again, we have maximum PE here. KE will be 0. In between, KE is 0. Okay. If I put another one in between here, between the maximum and minimum, then this one will have both. So over here, we're going to have both. Total energy will be KE plus PE in between, right? And so on. So that's the idea for kinetic and potential energy. Okay. Now, kinetic energy, the formula is the kinetic energy. The energy here is giving us 1/2 mv squared. That's the formula for kinetic energy. 1/2 times the mass times the velocity squared is velocity squared, velocity v. Okay, that's how you find kinetic energy. Okay, so for this question, so in which of these positions does a rolling ball have the maximum kinetic energy? Okay, so that would be C, right? To be C, maximum kinetic energy, the lowest level, maximum. So it can come in different forms, like a pendulum or this form as well. Okay, good. All right. As we go through this, I want us also to look at what we call data analysis. Data analysis, how to analyze data, right? So I'll be pointing some out to you. When you're analyzing data, it's very easy because you just have to read the problem and you try to understand it. It's like a comprehension. You don't have to have any knowledge about that particular thing. You read carefully, you answer the question, and the answers are always within the question, right? So we want to make some inferences for some questions and conclusions. Inferences, conclusions, and hypotheses. Those are things that you look out for when you're analyzing data. Okay, so we'll do that as we go on. Like look at question 23 through 25 on page 222. 222. Page 222. So read the question and then we'll answer 23 through 25. So it says, a chemical test for the presence of dissolved vitamin C is that the vitamin C bleaches a dark blue solution of indophenol.
I'm sorry, can you repeat the number again? Sorry.
Page 222, number 23 through 25.
Thank you.
Okay. So a chemical test for the presence of dissolved vitamin C is that the vitamin C bleaches a dark blue solution of indophenol. A student placed 1 ml of indophenol in each 6 different test tubes. Then a student added a different liquid, drop by drop, to each test tube until the blue color of the indophenol disappeared. As indicated in the following table, each liquid took a different number of drops to bleach out the blue color of the indophenol. And then we have liquid and the drops that are required. So lemon juice, 5 drops. Fresh orange juice, you have 20 drops. Cooked orange juice, 30 drops. Pineapple juice, 30 drops. Apple juice, 45 drops. Water, 100 drops, did not bleach it. Okay. And the question says 23. Which liquid had the highest concentration of vitamin C? So based on what we said, which one has the highest concentration of vitamin C?
D. Apple juice?
Okay, let's say apple juice, 45 drops.
What?
Apple juice, yeah, it has to be lemon juice, because lemon juice, 5 drops. Apple juice had 45 drops, right? So it means the lemon juice was very concentrated. So you needed just few drops to change the color of the indophenol. So it's more concentrated. It's 5 drops. So it has to be lemon juice. So C. Okay. And then 24. So according to the results, when orange juice is heated, its concentration of vitamin C is A, increase, B, reduce, C, destroyed, D, maintain at the same level. So look at the orange juice. Fresh orange juice, 20 drops. Cooked orange juice, 30 drops. So which one? What happened?
Is
Is it
reduced.
B? It reduced.
Yeah, the concentration reduced, right? Because we needed more drops before the color, change. So the concentration went down, reduced, correct. Good. And then 25, which of the following substances contain no vitamin C when the study began? A, endophenol, B, cooked orange juice, C, lemon juice, and D, apple juice. No vitamin C.
Okay.
A, correct. The endophenol.
Solution.
Because that one you are going to use that to test, so
Yeah.
that should contain any vitamin C to begin with.
Okay.
So you see what you've read. You don't need any knowledge. You just have to read the question carefully, and answers are within the problem. So it's comprehension, reading comprehension. Okay. So one thing I always advise people, you're going to have a lot of this type of scenarios, experiments. You just have to relax, read it carefully, and then apply your knowledge to whatever you've read. Don't answer anything outside, use your own knowledge. Use what is given, because comprehension. Stick to what is given. That's the key here. The answers are all in the question. All right, so number 26. 26 is a giveaway. You shouldn't get that wrong, because just a diagram and they're asking you which one is a longer shadow, So that was like a giveaway. If somebody gets it wrong, then it means that we need to check our eyes or something, Yeah, so they just want to test if you're careful in answering things. So what do you think number 26 is?
A.
Yeah, A, right? It's obvious, but it may not be obvious to some people. Yeah, I believe that's why they put it there. Nothing is simple. It'll be simple, but not simple. It is care, right? So the key word is be careful, when they give something. If you're not sure, put a paper there or pen there and see which one is the tallest. Yeah. All right, so that's, everybody had that one correct. Good. Okay. Okay, let's move on to page 224. Page 224. It says, which of these formulas represent an alcohol? So you see the classification I want to discuss. So it's which of the following is an alcohol? So which one do you think is an alcohol?
C.
I didn't hear what you said. Say it again.
C.
D.
Yeah, correct. D. That's correct. D. See. So you see the first one you have. Let's see if we can classify each of them. C2H5 or C2H5. Okay. If we look at this, which group is this one?
Alkene.
You have oxygen holding on to our groups. So this one is what anybody remembers. Look at your notes again. Oxygen holding on to our groups. ROR. That's ether. ROR, this is an ether. And then what are this one? C3H8. Anybody?
Alkane.
Yes, an alkane. Alkane. ANE. Because this is 2 times, like the hydrogen is 2 times 3 plus 2. Okay, the number of hydrogens. So single bonds between the carbons. And then CH3, COOH. The cool group. COOH group.
Carboxylic.
Yeah, so that's a carboxylic compound, carboxylic acid. And then the C2H5OH, and that's the alcohol that we said. Alcohol, correct. So alcohol. So this is what you want here. Okay. Alcohol. All right, so next time they will give you the other groups. So that's why I gave you all the different types. So if you see all of them, you know what you are working with. You know, identifying organic compounds. All right, number 34. It says, if a car's rate of change of velocity is negative, so the rate of change is negative. Sorry, change of velocity is negative. The car is A, speeding up, B, maintaining a constant speed, C, slowing down, and D, stopped.
D.
Slowing down.
Slowing down, yeah, negative slope, slowing down. Okay. Negative slope, deceleration, so slowing down. So it should be C. Okay, yeah. Okay, number 35.
Professor, please, I have a question.
Yes.
Yeah, negative. Yeah, as you said, the answer is C, right? But I thought the negative should be 0 as a constant stop.
Oh, that means that when it counts a stop, then, but here I said the rate of change.
Okay.
Right? If it's 0, so I said 0. The rate of change is negative, so it means it's dropping.
Oh, okay.
Yeah, it's coming.
It's changing or it's coming down.
It's coming down.
Okay.
It's coming down. You know, so it means it's slowing down. Deceleration.
Okay.
Yeah. Okay. All right. So you're welcome. Okay. 35. 35. It's balancing equation. So you should also know how to balance equations, as I said. You know. So look at that, and then if you can give me the answer to 35. You have NH2 plus dash H2 giving you dash NH3. Okay. And then it says, what is the coefficient of ammonia in the balance equation that has the smallest whole number coefficient? So we want the coefficient of ammonia. So this here.
Is it 1?
Okay, you had 1. Let's see if it's 1. If I put 1 here, let me see if I'm saying it's correct. If I put 1 here, how many nitrogens do I have? You look at the left side.
2. There's 2.
Yeah, you have 2, right? So it means it cannot be 1. So this cannot be 1 here. The left side has to balance the right side. So you want to try again.
So it has to be 2.
It has to be 2. Okay, let's say 2. If I put 2 here, let's see and see. 2 times, you have 2 of nitrogens. Is it correct here? We have 2 here. Okay, that's matching. Now, what about hydrogen? Hydrogen, you have 6 here. 2 times 3 of these. So 6 hydrogens on this side. You have 2 nitrogens here. We have 2 here, so 2 matches there. Hydrogen, that means hydrogen will need 3 to make it 6. So you have 3, you have 6 or 6 hydrogens, balanced. Okay. But this question is asking us for only this part here. So the answer is going to be, yeah, you always make sure the left side balances the right side. Okay. All right, so practice more on like balancing equations if you get a chance. Okay. All right, look at number 36 to 38. Again, diagram. I cannot stress diagram enough. The diagrams, don't skip them. Don't skip them. The experiment may appear long reading, but the answers are all there. So 36, look at it, 36, 38 through 38, let's see. So question 36 through 38 refer to the following graph of changes in population over a period of time. The graph represents the relationship of the actual population to the capacity of the environment to support it. And they have the diagram. Okay. Population and time, and it goes up and down like that. See, at what point is the population growth most rapid? Which one is most rapid?
3. Oh, C.
Okay, somebody said 3.
C. Sorry.
Yes, C is number 3, right? That's
Yes.
okay. That's what somebody said. Any other options?
B.
B2.
B2. I agree with 2. Now look at the slope carefully. You need to be a little careful here. Which one is steeper? 2, right? 2 rises faster than 3.
Right.
Yeah. So the steeper, the more steeper it is, means a rapid rise. You know, I mean, it's very subtle, very, small. You have to really look at it carefully. You know, so 2 is more rapid because the slope is greater than that of point number 3. So 2, most rapid. Okay. So it should be B. All right, then 37. At which point is there a decrease in population due to competition for dwindling food supply? Now the food supply is down, so now which parts do you have a decrease in population?
B4.
4, correct. 4, correct. You see, so all this like a negative slope. So again, think about the slopes. Positive slope increasing, negative slope dropping. You know, that's the idea. So 4 is dropping. Okay, correct. So D, right? So 38. For which type of organism is this graph believed to be typical?
I'm guessing D. It's in dog.
Okay, your guess is correct. All organisms, including human beings. Perfect, is correct. Good guess. All right. Now, so what this means is that if you, let's say, let me use a bacteria, for example. If you have initially, let's say I have the petri dish, right, in the lab, and I have a bacteria placed on it. Initially, now it begins to grow fast. It starts growing, so there's rapid growth, growth. So that's why you have like a rapid part here. Then as they grow, it gets to a point where you have many colonies. Now the food supply, you're not adding anything if you're not adding any food in here, no nutrients. Okay. So what's going to happen? It gets to a point where the growth will become stagnant, it becomes or stable. It's not going in the region of change. So some of them will have to die, die, reproduce. So it gets to like a stable population, die, reproduce, die, to maintain whatever supply that you have here, right? So after some time, if all the nutrients have been used up, remember we're not adding anything, no nutrients coming in. If all supplies have been used up, what's going to happen? It's going to be survival of the fittest. Now they begin to die off, and they're going to die off, So that's how the diagram, that's why you have up and down, but it comes and so on. And the same thing can happen to human population. If we don't have any source of food coming in, and there's only the only food you have is what you have, nothing else, nothing is coming in, nothing going out. The same thing can happen to us, So all organisms go through that stage of rapid growth, then becomes steady growth, and then it begins to drop. Okay. All right, great. Okay, so you see again, diagram. Answers are all in there carefully. Okay, number 40. A substance with a pH of 8 is A, strong acid, B, weak acid, C, strong base, and then D, weak base.
D.
Yeah, pH of 8. So that is a weak base. It's more than just above 7, right? So it's in the weak base zone. So D, correct. Okay, number 42. Which of these substances forms an alkaline solution in water? Alkaline solution. Remember, alkaline is the same as the base. Okay. And then you have MgOH2, and then B, H2SO4, C, MgSO4, and D, NaCl.
B.
A, correct. So you have magnesium hydroxide. Okay, because if you put this in solution, it's going to give you magnesium, usually 2 plus OH. It produces hydroxyl ions in solution. Because of this, that makes it a base. It produce OH in solution, correct. Okay. All right, great. Another experiment question. The answer is in the question. So read it carefully. Questions 43 to 44. 43, 44. Okay. So a student was testing the colored materials in spinach. He ground up some spinach leaves in acetone. He then filtered the mixture and obtained a dark green filtrate. He placed a spot of this filtrate on a spot X on a strip of filter paper. Then he hung the dried paper in a tube containing a mixture of petroleum ether and acetone at the bottom. After a while, he observed moisture creeping up on the paper and several bands of yellow and green color. Question 43 says, the experiment uses the technique of A, fluorescence, B, photosynthesis, C, centrifugation, and then D, chromatography.
D.
All right, somebody said A. Any other options?
D.
D. All right, so the answer is D. Why is the answer D?
The chromatography. Chroma is the component in the plant. Plural. I don't know. I'm just guessing.
Well, good, that's a good guess. Right, the chroma has to do with color, right? Chroma.
Yes.
But anything that's chroma key, chroma something, you know, root of words has to do with color, you know. So that is a good thing you're picking up. So the color, the fact that like have color somewhere, you know, tells you really chromatography, study of coloring, like a color to determine substances, you know, identify substances using color to chroma. So in the lab, that's what they do. You use what we call electrophoresis. Okay. You put what it is like you have this gel, sometimes a paper, and you have gel chromatography, sometimes paper chromatography, and so on. But the whole idea is that you have that, let's say this is a paper, then you put a known substance here and maybe an unknown substance here. Then you put this in the solution, like what you have the acetone that you described right here, you know, then apply electricity to it. Or sometimes they don't even apply electricity. It is just like it rises, the water flows or climbs out the paper, and as it climbs the paper, it separates the various colors, components into bands, all right? So if it's a known one, and let's say this is this, they have an unknown one. You put an unknown one here, it's also going to do the same thing. You have different bands, right? So you can compare. You can compare this to the known and know, okay, this is the same substance. If it's not the same, then you also know. You know, that's a chromatography that we're talking about here. You spray it later with something that will give you a color that you can use to identify them easily. And it's all based on like different sizes of the molecules, right? So think about pouring water. Let's say if I have something a big object here and another small object, and I pour water, which one is going to move faster? The small one is going to move longer distance than the other one. So maybe that will be here, and the heavy one will be somewhere there. You know, the same thing. So the larger molecules will travel shorter distance, whilst the longer one, smaller ones will travel further away. You know, so they will separate. They will do like a different bands at different positions. That's the idea of this experiment. It's just to separate things. And then once you spray with a chemical, it gives you a color that can help you identify easily. Then 44. The student should conclude that. So what do you think the student should conclude? A, spinach contains two kinds of chlorophyll, green and yellow. B, spinach contains more than one kind of pigment. C, all organic pigments are soluble in acetone and petroleum ether. And then D, all organic pigments migrate on filter paper at the same rate.
D.
A.
It contains two kinds of chlorophyll. Okay, can you support your answer with a sentence in the passage? Just a key, the passage that can give you the answer.
The last sentence, it has his observation.
All right, the last sentence says, after a while, he observed moisture creeping up the paper and several bands of yellow and green color. Does it change your idea or your answer? It says spinach contains two kinds of chlorophyll, green and yellow. Does it match what you've read? Or would that convince you to change your answer?
Change the answer.
Okay, which one will you choose now?
B.
B, spinach contains more than one kind of pigment.
Excellent, excellent. So you see, the answer is in the question. That's what I want to point out to you. When you see this type of problem, the answer is in the question. You just have to read carefully. So the key word here is several bands of yellow and green color. You know, they didn't say just two. Otherwise, that would be, you know, it's just two for, but it says several. So the only conclusion you can make here is that spinach contains more than one kind of pigments. I hope you get my reasoning. Okay, that's the way you should be reasoning through the problems. You know. Okay, good, several. So B is the correct answer here. Okay. All right. Let's look at this one here, which is okay. Page 227. 227. Number 53. Which of these biological processes includes the other three? A, cell respiration. B, Krebs cycle. C, electron transport chain. And then D, anaerobic splitting of glucose. So one of them has all the other three in it. Anaerobic splitting of the glucose is the glycolysis. So which one contains all the other three?
I'm guessing A.
Hey, you're right. Good guess. So cell respiration, remember I said it has all the component has glycolysis, Krebs cycle, and electron transport chain. They're all under cell respiration. Okay. So A. Okay, 54. That's what I just asked earlier on. A 5-year-old and her father each lifted identical chairs from the floor to a tabletop. Which person did the most work? Now you know the answer. So A, the father. B, the 5-year-old. C, they both did the same amount of work. D, not enough information is given.
C.
C.
Yeah, C. Yep, they see the same, both work, same amount of work. Yep. Okay, so 55. An excess of which of these ions tends to make a solution acidic? A, chloride. B, hydroxyl. C, hydronium. And D, sodium. Acidic.
C.
C, yeah, hydronium. Remember hydronium, H3O plus, H3O plus, hydronium. Yep, basic acidic. Okay, let's see if I have another one here. Okay, page 229. 229. Number 5. 229, number 5. More energy is used in pushing a box up along an inclined plane to a height of 4 meters than in lifting the box straight up to the same height. This is because A, more force is needed in pushing the box than in lifting it. B, work is done against friction in pushing the box along the plane. C, the box moves a greater distance when pushed along the plane than when lifted. And then D, it takes more time to push the box along the plane than to lift it. You're pushing the box up an inclined plane. What happens here?
B.
Did you say A? Did you say A?
B.
B.
Oh, B. Okay, B. Okay, yeah, B is correct. B, that's correct. So work is done against friction. You are pushing on the floor, so there's friction, opposing force, in pushing the box along the inclined plane. So B, that's correct. Excellent. Okay, page 230. Page 230, look at number 8. Which type of circuit is shown in the diagram?
Parallel.
Open circuits, B, complex, C, series, D, parallel. Yeah, parallel circuits, right? That's an example of parallel circuits. Parallel. Number 9, the device shown in the following circuit diagram consists of copper wire wrapped around an iron rod, and connected to a switch and battery. When the switch is closed, the device could serve as A, transformer, B, an electromagnet, C, a motor, and D, a generator.
A.
Okay, look at the diagram again.
B.
B is an electromagnet. Electromagnet, right? Once you close the switch, current will flow, and then you have the ion becoming a magnet. So you have electromagnets. Okay. So B. Okay, number 10. I spoke a little bit about number 10. I give an example like that earlier on. So he said the following graph shows the motion of a car over a 10-second period. Then during which time interval did the car cover the greatest distance? You have 0 to 2, 2 to 4, 4 to 6, and then 8 to 10. So think about what I discussed earlier on, using the boxes to estimate the area. Greatest distance. Okay, which one?
4 to 6 seconds.
Yeah, 4 to 6 seconds. That's the greatest, right? You have two boxes, and the curve in that interval, two boxes in that area. Okay, whilst 0 to 2, you have half of a box with a triangle. 2 to 4, a box and a triangle, half of the box. Okay, and then 4 to 6 is two boxes. 8 to 10, you have half of a box, which is the triangle. So C is correct, greatest. Okay. All right, number 11, I believe you can do that one. A student wants to grow a bacterial culture. Which of these environments is best suited for growing most kinds of bacteria? a lighted window at 72 degrees Fahrenheit, a refrigerator at 45 degrees Fahrenheit, an incubator at 37 degrees Celsius, a freezer at 10 degrees Celsius. Which one will be best?
C.
Actually, C.
Yeah,
37,
don't
that the body temperature, right? 37 degrees is like a normal body temperature. So you need an incubator around that temperature. Your bacteria love a body temperature like that. Okay. Number and page 232. Page 232. Look at number 16. So again, an experiment question. There's something called a control. In every experiment, there's a control. The control is the one that you omit whatever you're testing, right? The the factor you're testing, you omit that in that group, or a control group. So a student wanted to test the effect of different sugars on the growth of a certain mold. The sugars to be tested were glucose, fructose, and sucrose. 1 gram of each sugar was placed in a tube of 10 ml of water, and a bit of the mold was put in each of the 3 solutions. To add a control to the experiment, the student should also have A, made 2 setups of each of the 3 sugars. B, tested ribose and galactose. C, made 1 setup of just water and mold. And then D, kept the 3 setups in the light. So we're talking about control experiment here, control group.
A, made 2 setups of 3 sugars.
You said, you said that again. I didn't hear you. Well,
A, made 2 setups of each of the 3 sugars.
Okay. Remember the control in the control group, you want to omit the factors that you're testing. All right. Let me give you an example. Like if I want to find out whether taking this class is good or not, right? Or whether it helps you pass the exam. I have to have what we call a control group. So I'll have 2 groups, group 1 and group 2. The first group, I expose them to the workshop. So like the way we are doing now, you're exposed to the workshop. Now this group, no exposure to the workshop. Okay, so here you have exposure. And afterwards, we give all of them, both groups, the same test. You test them. And then see which group is going to do better. If this group does better, group 1, if they do better, it means that the workshop is good. You know, if they do better than group 2, significantly, that means the workshop is beneficial. If the groups are performing equally well, then we say, okay, they may not be too effective. You know, the test with the study may not be too effective, and so on, right? So you have to omit what you're testing in one group. So which answer do you think will be correct here?
C.
C, yeah, C will be more appropriate here. So the control group. So the one test tube, you have your glucose, another test tube, your galactose, another test tube, you have your fructose. So have one test tube that will not have any of them, just water and the mold. So here you have glucose and your mold in each of them. So eliminate all those things and see whether it will grow well like the other ones. You know. If it doesn't, then it means that you need those nutrients. Okay. So C is correct. Okay, number 17. Vinegar is a common antidote for injection of lye. What is the chemical process underlying these treatments? Vinegar is a common antidote for the ingestion of lye. What is the chemical process underlying this treatment? A, digestion. B, alkalinization. C, oxidation. And D, neutralization.
Neutralization.
It's neutralization. Neutralization. Right, correct. Now, vinegar is an acid. It's an organic acid, acetic acid. That's the name. And then lye is a base. So acid plus base, neutralization, they form salt and water. Okay, good. Neutralization. All right, number 18, again, you don't need any knowledge. If you read it carefully, you know what it is. It says, answers are, it's a conclusion or make inference from the reading. You can deduce from the reading. So it says, undisturbed layers of rock were examined. Mammal, fish, and bird fossils were found only in the upper layers. Then fish were in the layer beneath those, and neither fish, birds, nor mammals were in the deepest layers. This tends to support the hypothesis that A, vertebrates always coexisted with invertebrates. B, fish were the first vertebrates to evolve. C, all vertebrates evolved at about the same time. And D, birds evolved before fish. So analyze and see what's the answer. So the key fish were in the layers beneath those, and neither fish, birds, nor mammals were in the deepest layers. So what are they trying to prove here?
B.
Well, so B, so it means fish were the first vertebrates to evolve, according to what they found here, because they are in the deepest layers. You know, like they died and the other ones came and then, you know, and died and so on. So fish, B is the answer here. Fish were the first vertebrates to evolve here. Okay. All right, so we're seeing a couple of problems. Page 234. I want us to round up and go to the math shortly. 234. Number 21. I explained that already. So this is that's a question that I talk about. 21. Yeah. So they all hit the ground simultaneously for this one. Okay, number 22. Blue litmus paper would turn red when placed in a solution having which of the following pH values?
D3.
Oh yeah, it's correct. You got it. So 14, 12, and 7, and 3. Okay, it's 3. Because blue litmus becoming red means you are dealing with acid, right? Acid. So 3 is acid pH. Okay. I'll skip number 23. 24. H2SO4 is an example of, we know that already, salt, base, acid, and halogen. So that's an acid with H2SO4. We saw them. Okay. What about 25? 25, it's also making inference. Many people believe that some trees drop their leaves in the late fall because the temperature is near freezing. Which of the following statements least supports this idea? Least supports this idea. A, maple trees in North Minnesota drop their leaves in late fall. B, maple trees growing near the city lights stay green longer than those far from the light. C, maple trees pass through a time of near freezing before they bud. And then D, maple trees in southern Florida drop their leaves in late fall. So least supports.
B.
D, maple trees in South Florida drop their leaves in late fall. All right, yeah, that's least supports, that's correct. Okay, yeah. So it means that it's not because of the temperature that their leaves are dropping, right? So freezing, late fall, they drop their leaves, freezing. Florida too is not, the temperature is still high, but they're still dropping their leaves in the late fall. So this list supports the idea that temperature affects. Okay, good. If you look at 26 to 27, it also talks about, like the diagram, if you go through, again, is based on the table that you have here. Okay. So I'll leave that one out. I want us to go back to the math. So look at number 30. Number 30 is a diagram on the plant, 236. I spoke about that too. Number 30. You had a plant growing towards light.
Phototropism.
Yeah, phototropism, right? So we know that now. Okay. Okay, one question on page 238. Page 238. Number 36. It's a diagram, a graph. It says, this graph shows an object that is A, at rest and then moving at a constant speed. B, moving at a constant speed and then accelerating. C, at rest and accelerating. And then D, accelerating slowly and then accelerating rapidly.
B as in boy.
B.
B, yeah, it's moving at a constant speed. You know, it's like a zero slope and then accelerating, positive slope. So B, correct. That's correct. Okay, good. Page 239. Page 239. Number 44. 44. It says, which formula represents a carbohydrate? Yeah, they gave you all those things there. So think of the equation that photosynthesis and respiration thing.
D.
Yeah, D, C6H12O6. That's the formula for carbohydrates, correct. And then 46, I also mentioned that, Ohm's law. So Ohm's law is used in the study of A, electricity, B, mechanics, C, thermodynamics, and D, optics.
Electricity.
The electricity, Ohm's law, V is equal to IR. V equals to IR, okay. Now 47, make a guess. A cloud chamber is a device used for A, studying the formation of weather systems, B, recreating the atmosphere in primitive Earth, C, treating a respiratory infection, and D, studying charged particles.
A.
D. So D, the cloud chamber is to study charged particles. Charged particles. Okay. All right, so I think we've seen a lot of questions. There are more that I would like us to see, but I want us to do something else. Okay. There's one thing that I didn't mention. Look at page 241. 241, number 60. I didn't mention that, so I'll mention it briefly. Number 60. See, a compound that can act like an acid and a base at the same time, right? As an acid or a base. We describe that compound as amphoteric. 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 That's the meaning. Compound that can act as an acid or a base at the same time. Amphoteric. An example would be something like sodium bicarbonate. It can be an acid, it can act as a base. So amphoteric compound. Like amphibian, ampho. It can be here, it can be there. Right? So A for number 60. Okay. So you can add that to your notes. Okay. All right, so I think question number, page 244. 2 calculations on electricity and what do you call it? Motion. Then we'll end on that one. Number 12. 244, number 12. Said an object is traveling at a constant velocity of 100 meters per second. How far will it travel in 20 seconds? Velocity, time. You want to find distance or the displacement. So what will be the
1,000.
so 2,000? Yeah. So you have to velocity times time gives you the total displacement, right? So here is 20 times 100, so 2,000 meters. Correct. That's correct. And then see number 14 has to do with the power. Number 14. A 36 lamp is operated by a 9-volt battery. How many amperes of current are flowing through the lamp? So remember, power is equal to voltage times current, right? Remember that one. P is equal to VI. I told you we'll come to that. So use that to answer 14. So what's the answer here?
Four.
Yeah, it's 4. That's correct. 4.
4A, yeah.
4 amps, yeah. But this is 36. The voltage is 9. We don't know the current. So I divide by 9, divide by 9, and then you get I to be equal to 4 amperes. Amps. All right. Good. All right, great. So at least we've seen a lot of questions. There are more questions when you go back. Try 247. You see the forces. We did a lot of that. You see a graph on, when we come next week, we can look at them again, and then SI units on the next page and so on. So I expect you to be able to apply today's knowledge to all these questions, right, So hopefully when we come next week, if there's time, we'll look at more of them again, right? Okay, as usual, I always want us to make sure we are also cover some math. Next week, I'll make sure we do more math. Okay, so let's go back to the math in practice a little bit. And then most of the math becomes like same thing all over again. So you're gonna get it fully. Okay, so we stopped on number 10 last time. Page 105, number 10. That's where we stopped. So let's move on to page 106. 106. And then we'll continue as far as we can. Okay. Page 106. So please try the problems, number 11 through 17, and then we'll discuss at some points. Number 11.
You don't eat that.
Okay, so what do you get for the first one?
B, 8.
A, okay. No, say 8, right?
8, yes. B.
My answer is D.
Let's see.
My
What's
answer
the
is
square root of 64?
8.
That's 8, and then divide by 4.
Oh, I do that.
So we should have 2.
2.
Yeah, 2. Okay, all right, number 12. The daily
D.
dose of, oh, you did already?
Oh, we didn't answer all. Sorry.
What do you say is the answer?
C.
C, 295.
95.
Okay, let's see. So what did you do? The daily cost of patient care in a hospital is $250. The cost rises by 18%. What will the daily cost be? So let's all do it together so that at least if somebody didn't get it right, the person will get it right next time. So can you tell us what you did?
250 times 0.18.
0.18. Okay, correct. So you find 18% of 250. That's what you're doing. 18% of that. So 0.018. Okay. And then what do you get?
And then you get 45, and because the cost rises, you add 250 to 45.
250 plus 45. Correct. So you're adding on. And then you have a $295. Correct. Okay, so this is a two-step problem. Find 18% of what you've been given, or the original cost. 18% of that by multiplying by 0.18, or you can do 18 over 100, times 250. You get the same answer. And then you add on because it's increase percentage. Perfect. Okay, correct. Correct. So this is one type of problem that you also get in terms of percentage increase problems or percentage decrease. If it decreases, then it subtracts. Okay, number 13. Number 13, 0.022 divided by a question mark is equal to 0.55. Now, if you have a question like this that is confusing you, write it in the algebra form, right? If you can write 0.022 over x, a certain number, is equal to, if this form is confusing you. And then you can solve for the x. Because sometimes some people don't know whether you have to multiply or divide this, and they get confused with all that. So it means that your x will be equal to, say if you do, that tells you they have to divide. So anytime you're confused, you can do that. Algebra format.
Or another way, you can divide like all the options and then you can get your answer.
Exactly, right? You can work backwards. So that's a back solving. Back solving. Back solving. Always you can rely on that. It's solving. Good approach. Okay. So a lot of questions, if you're stuck, do a back solving. One approach. Okay. So what do you get here if you do that?
$12.
0.4.
14.
What is it? It's a 14. You have 25, 0.4, 0.04, 0.0121.
D as in dog?
0.04.
Yeah, 0.04. 0.04. 0.04. Okay. All right, let's try number 14. Number 14 is a rectangle. So if you're doing these problems, you can draw diagrams to help you. Where problems, sketch. Rectangle, then they give the perimeter. P is given as 36. The width is given as 6. They said find the length, how long? You don't know this part here. So ask yourself, what's the relationship between the width, length, and perimeter? Rectangle, we know that the perimeter is given by 2 times the length plus 2 times the width, right? For a rectangle, perimeter of a rectangle. So now you can use this information to answer this question. So take like a minute to try that.
D6.
No, I don't think she'll be 6. Because our perimeter is 36. So it is 36, right? So it's 2 times, we don't know the length. So the 2 times, we don't know x, let's call it x, plus 2 times the width. The width is 6. If you put this together, the total perimeter is 36. So this is 2x plus 12 is equal to 36. 2x is equal to subtract 12 from both sides, that's 24. And divide by 2. So x is equal to, should be 12. 12. So in other words, what you're doing here, you see you're adding the width twice. So multiply 6 by 2, but this side is also 6. And this is also x. So 6 plus 6, which is 12, subtract from 36, whatever you get, divide by 2. Split in 2 parts to get the length. And that's the algebra approach. Yeah. To twice the length plus twice the width. Okay. All right, number 15. Be careful with number 15. If you don't do it right, the answers will be there. They covered different approach that people do it. The difference between the boiling point and the freezing point of mercury is 396. The boiling point is 357. What is the freezing point? Boiling point, freezing point. Boiling point.
A.
I didn't hear what you said.
A.
Try again.
It's C.
It's C. It's C. All right. You know, they covered all the grounds, the mistakes that people will make in this one. Okay. Now, the first, you have to read the question. Say the difference between the boiling point and freezing point, right? So difference, you translate the way it appears. Okay. So we get a boiling point minus, that's subtract the boiling point first, minus the freezing point is equal to the difference that they gave was 396. So this is the translation of the difference. This minus that is equal to this. You translate the way it appears. Okay, then the boiling point is given as 357. So this minus, we don't know the freezing point, should be equal to 396. So if we solve, we move this over here. So it's negative f will be equal to 396 minus 357. So you have negative f is equal to 39. Since you're solving for f, you have to multiply both sides by negative. So you can f become positive and then have negative 39. Okay. So translate the way it appears, difference. Okay. Okay. Number 16. Prime numbers. So we have to know the definition of prime numbers. So a prime number. Okay, so that is what? A number that has only two factors, correct? A number that has only two factors. That is one in itself. Okay, prime factors. Okay, so which one do you think is the set that is not prime factor? Not. It's not. If you have the answer, you can just give us. 5 and 13 is there a set of prime numbers? Yes.
It's
So the first one is prime numbers, right? 2 and 7.
Yes.
Again, prime, yeah. So because 2 is only 2 times 1, and 7 is 7 times 1, nothing else. 19 and 27.
Yes, they are.
Yeah. No, it's not.
No, 27 can be.
Yeah, so 27 is not, all right? So that should be the answer. So C. C is not, they are not prime numbers. Like 19 is a prime number, but 27 is not a prime number because you have what? 3 times 9, and you also have 27 times 1, right? So it has many factors there. So the answer should be C, not the set of prime numbers. Okay, correct. Okay, let's try 17, fraction, dividing fractions. So this will be good to use to explain dividing fractions. Okay. Remember, when you're dividing fraction, you keep the first fraction times reciprocal of the second fraction. Okay. So if you can try this before we do it together. All right, so what we have here, you have 3/4 divided by 6/1. All right, that's what we have. Okay, I put this for 1.
The answer is D.
Okay, that's correct. Okay, so as we said, keep the first fraction, change the division to multiplication, and then take reciprocal of the second fraction. So now 6/1 becomes 1/6. So this is going to give us 3 here is 1, 3 here is 2. Nothing else to reduce, so multiply horizontally. So 1 times 1 is 1 over 4 times 2, and then that's 8. So it's 1/8. So the answer is D. Keep the top fraction times reciprocal, or the denominator. Okay, number 18. So assume that the ratios of deaths resulting from heart disease to death resulting from cancer is 5:2. So they give us a ratio. So our right ratio, remember ratios and proportion. So 5 deaths from heart disease. So I'll say heart disease, 2 deaths from cancer. So that's the ratio given. So once you see ratio, think about proportion. Ratio goes proportion. So you can set out the same ratio here, have the heart condition here, and the cancer, same ratio, match. Then what have you been given? For every 100 deaths result for cancer, so you have cancer here, 100. You want to find how many deaths for heart disease, like this. So you have a proportion that you can solve. So if you have a proportion, then use a cross product. So 2 times x, so that's 2x is equal to 5 times 100. Okay. And then you can divide by 2 and divide this by 2. And you get the answer. You're allowed to use a calculator on the test, so you can multiply and divide. But if you're like me, who likes to work things without calculator, then it means I have to cross this out 1. This is 5, 0. If I multiply, I get 250. That's your answer. So proportion, as I keep saying, very, very handy. Master proportion. So please try number 19. 3.5% off. Off is multiplication.
D.
490.
490.
Yeah.
Okay. All right, so you can write it like the 3.5 over 100 times 1400. Or if you like to use decimal, then that means that you have to move this decimal point 2 places to the right. So you have to do 0.035 off, so times 1400. You come out with the same answer. What is it? What's your answer again?
It's
My
40.
answer is 49.
Yeah, 49. So the zeros will cross out. So you have 3.5 times 14. So that should be 49. If you do the decimal, you come with the same answer too. Okay. All right, number 20. Number 20 is the type of questions I know you all like. Was it like a nesting type of problem? So try and figure it out and let me see. So a baby's temperature dropped an average of 0.15 degree Fahrenheit per hour. over a 12-hour period. If her initial temperature was 104.3 Fahrenheit at 3 p.m., what was the reading at 3 a.m.? So what would be the first thing that we should do?
Multiply.
Yeah, we need to multiply something. So what by what?
12 times 0.15.
Okay, so 12 times 0.15, correct. So you have to, because it said over per hour, over 12 hours, right? So we need to find a total amount of drop. So it's 1.5 times 12. Okay, and what do you get for that?
1.8.
1.8. Okay, so 1.8 is a drop. Now the initial temperature was 104.3 degrees Celsius. Sorry, Fahrenheit. So, and that dropped by 1.8. Yeah, 1.8 drop in temperature. So now what do we do here? Subtract, right? You gotta subtract. So 1.04 minus 1.8 to get a new temperature. So you have your 120 points. What was it? 1.2.5, right? Degree Fahrenheit. So that would be the new temperature. Great. 21 has to do with greatest common factor, GCF. Greatest common factor. So to find a GCF, you have to take each number at a time and then find a GCF of each of them and then the variables, all right? So begin with the coefficients. So between, let's see. Okay, so we have 3 and 12. So between 3 and 12, what would be the greatest common factor?
12.
Okay, GCF is 12, right? And then you take a cube and a to the power 4. What would the GCF? The GCF is always the smallest exponent, the one with the smallest exponent, right? So the GCF is a3 to the power 3. And then between b squared and the b, the GCF smallest exponent, so b. And then between c and c cube, your GCF will be, there's a c. So use the one, the smallest exponent. So for the whole thing, a GCF that you want will be equal to, oh, no, this one is wrong. The GCF for 3 and 12 is 3. That is 3 here. Should be 3. GCF is 3. Okay, so for the whole thing, the GCF will be 3 and then A is cubed, B, and then C. So that is a GCF. GCF. 3A cubed BC. Okay. So that makes the answer C. C. Okay. So always use the smallest exponent for the variables. And then GCF, the greatest common factor, the greatest number that can go into the numbers given to you. Okay. So 3 and 12, largest number that can go into 3 is 3, and it can go to 12 is 12. Okay. Okay. All right, number 22. 22 says a 64-ounce bottle of medicine is on hand. Each person X receives 5 ounces. Which of these formulas shows the amount of medicine left in the bottle? Amount left. Okay. So which one will you select as your answer? M is 64, M is 64 over 53. B, M 32 over X. C, M is equal to 5X minus 64. And D, M is equal to 64 minus 5X.
Is it D?
Yes, D is D. Okay.
Yeah.
Right. Because you have to know the total amount given to the people. There are X number of people, and each one receives 5 ounces. So the amount given out to all of them, the X number of people, is 5 times X. That gives the total given to them. What are we starting with? Initially, you have 64 ounces. So if you give out 5X, how much will be left? That's how the question goes. So the amount left, M, is equal to what you have at the beginning minus what you give out. So this is how it should be. Okay. So that's why it's D is correct. Okay. Perfect. All right. So number 23. Number 23, you don't have to waste your time doing certain things. You can make your life very easy in 23. Okay, it says labels measuring 2.5 by 1.5 are to be cut from a row measuring 48.3 by 1.5 inches. What is the maximum number of labels that can be made here? Okay. Amount of labels that can be made. Okay. So when you read this, what should come into your mind is the area. You know, to know the area of the small piece, and you have to know the area of the bigger piece that you're dealing with, the row that you're dealing with. You need to know the total area. And how do you find area? The area is length times the width. You multiply what is given, right? To find the area. But I'm not going to waste my time multiplying everything out, okay? So you have 48.3 times 1.5, right? That would be the area for the bigger one. What do I have to do? I have to divide the big area by the small area. So I know I have to divide this by that. So the large area divided by the small pieces that you want. You're breaking it down. So breaking it down means you have to divide something. Okay. But if I have to multiply this, it will waste too much time, right? And I have to, but I can see something common here. What do I see in common? I see 1.5. So I can quickly get rid of this by crossing them out. Right? So I've saved time going back to multiply those things out. The common factors, so cross them out. Now I have to divide, there's the 48 divided by 3/4 divided by 1/2. That's all I have left here. 48 3/8 sorry, let's say 3, it's 3/4 divided by 2.5. That's what I have left. And how do I divide fractions? If this is a mixed number, I have to change to improper, what do you call it? Fraction first, right? Improper fraction. If you like, you can, if you want to use a calculator, that will also be fast. 3/4, you can change 3/4 to what do you call decimal, right? 3/4 to decimal, then that would be what? That would be 48.75. You can do that. 3 divided by 4, that's 0.75. And then divide this by 2.5, that's 2.5. Okay. So if you divide this, that should give you the answer. Okay. So that, I think it's around 19 or so. So check that to a calculator. I think it should be 19. 19.5, right? So 19.5. But then since we are dealing with what do you call it? Pieces, number of pieces, we can have like half of that number. So it's up, you have approximately 19. 19. Yeah. So 19. Approximately 19. So that would be the decimal way. Okay. So if you want to do that, what do you call it? The fraction way, then you have to change this to improper fraction first. So multiply 4 times 48. 4 times 48. So that will give us, let me check.
192.
You had a 192?
195.
Okay, then plus 3. So that will be 195 over 4 divided by, this is 2.5. 2 times 2 is 4 plus 1, that's 5 over 2. Okay, since you are dividing two fractions, you keep the first fraction, change to multiplication, and then reciprocal of the second one. So 2 over 5. And then we can simplify what you have here. 2 into itself is 1, 2 here can be 2. I know 5 can go here 1 time, 5 can go here, that is 3, that's 15. And then you have 3 left. So 4 left, so 39. So you have 39 over 2, which is 19.5, and then you have the same answer, 19.5. 19.5, which is approximately 19 pieces. Yeah. So that would be the fraction way, you know. But I think since you're allowed to use calculator, you have to, you know, you can use decimal too. You know, change to decimal, you can easily use that. You know, unless you don't have calculator to use. Great. Okay, so now 24. 24. 24 has to do with a circle graph. So remember, for circle graph, the total degrees is 360. 360 degrees is the total number of, you know, 360 degrees for circle. Okay. So anything that has to do with circle graphs, think about 360 as a total. Okay. So 24 says a circle graph indicates 3/4 of the hospital budget is spent for staff salaries. How many degrees of the circle represents staff salaries? How many degrees of this represents staff salaries? Okay. So it's going to be 3/5 of 360. That's what you're trying to find. And that means that you have 3 over 5 times 360. And then you have 3/5 of that. And then you get your answer. You don't want to make any errors, you can put this over 1, and then you can multiply them out horizontally. Okay. Or you can reduce to lowest terms. And then you have your answer. And 5 here will be 1. 5 here will be, that is 6, 7, 72. So nothing else to reduce. So multiply horizontally 72 times 3. So you have 216 degrees. But you're allowed to use a calculator, so you can just multiply 3 times 360, get the answer, and divide by 5. 5 times 1. Same answer. All right. What about 25? 25. It's already 2. Okay, we can maybe pause on, we can pause on 25. We can pause on that. Let's see. Today I really wanted us to finish this one. I think next week I'm going to switch a little bit so we can catch up on the math. Okay. All right. So it's already 2. So we'll pause. Let's pause on this, and then I'll continue from 25. We'll finish the test 1 so that we can work on test 2. Next week. We'll definitely try to catch up. I want to catch up on the math next week. Yeah. Okay. So we can pause here for today. I know we are all tired. You know, my throat is all dry. So. All right. So any questions? We'll continue with 108, page 108. Let's mark that page. We'll continue from there. But please keep working ahead. Any questions before we break for today?
No.
No.
Professor,
When will you